long before the Earth looked anything like it does today, before the Atlantic Ocean stretched between the Americas and Europe, before Asia towered above the Indian Ocean, and before Africa drifted into its familiar place, there was Pangaea. Imagine a time when nearly every continent we now know was fused together into one colossal landmass, a supercontinent so vast that it held deserts, mountains, rivers, and ancient forests all in one sprawling stretch. Dinosaurs roamed freely across what would later become separate continents. Oceans lapped only at the edges of this massive world island, while deep beneath its surface tectonic forces were quietly setting the stage for Earth's future. What made Pangaea form in the first place? Why did it break apart? And what secrets still lie buried in the Earth's crust where it once held together? Before we begin this prehistoric journey, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below and settle in for a fascinating ride to the early days of our planet. Imagine a time when the entire surface of the Earth was ruled by one gigantic piece of land, an enormous supercontinent that stretched almost from pole to pole. This supercontinent was called Pangaea, and its story takes us on a journey through hundreds of millions of years of Earth's deep past. The tale of Pangaea begins during a time known as the Paleozoic era, long before dinosaurs ever walked the Earth. The process of Pangaea coming together didn't happen overnight. It was an incredibly slow but powerful movement that started around 335 million years ago, during the Carboniferous period. At that time, there were already a few large landmasses on Earth. Two of the biggest were called Gondwana and Laurasia. Gondwana was made up of what we now know as South America, Africa, Antarctica, Australia, and India. Laurasia included areas that would one day become North America, Europe, and most of Asia. Over millions and millions of years, these massive chunks of land slowly drifted toward each other, pushed along by the forces deep inside the Earth. Bit by bit, like a giant jigsaw puzzle, the pieces came together, closing up ancient oceans and joining into one massive landmass, Pangaea. Pangaea reached its most complete form during the Permian period, and it stayed that way into the early part of the Triassic period, a stretch of time between about 299 million years ago and 200 million years ago. This was Pangaea's golden era, when most of the Earth's land was gathered in one huge clump. But even something as mighty as a supercontinent doesn't last forever. The same powerful forces that pushed the continents together eventually began pulling them apart. Around 175 million years ago, during the Middle Jurassic period, cracks began to form in Pangaea's surface. These cracks grew larger, turning into deep rifts and eventually into vast oceans. Over time, these growing gaps split the landmass into smaller continents, leading to the familiar shapes of North America, South America, Africa, Europe, Asia, Australia, and Antarctica that we know today. This was the beginning of the world as we now recognize it. So why is Pangaea so important, even though it existed so long ago? The answer lies in the huge impact it had on Earth's geology, climate, and life itself. When Pangaea formed, it caused the Earth's crust to bend and break in dramatic ways, giving rise to some of the world's most ancient and majestic mountain ranges. For example, the Appalachian Mountains in eastern North America, the Caledonian Mountains in Europe, and the Ural Mountains in Russia all formed because of the powerful collisions between these ancient continents. These rugged peaks are silent storytellers, still standing tall as reminders of Pangaea's might. Later, when Pangaea began to break apart, something just as incredible happened. New oceans were born. As the land pulled away, molten rock from beneath the surface created fresh ocean floor, especially where the Atlantic Ocean began to form. That process continues even today, very slowly pushing the continents farther apart and constantly reshaping the planet's geography. The climate during Pangaea's time was also extreme and unusual. Because this supercontinent was so enormous, much of its interior was far from the oceans, which meant there was no sea breeze to keep temperatures mild. Summers were burning hot, winters were freezing cold. The inner regions of Pangaea were likely dry, dusty, and desert-like. The ocean that surrounded Pangaea was called Panthalassa, a vast and deep superocean. Because there weren't many smaller landmasses breaking up ocean currents, warm water could move freely around the equator, which may have made the Earth even hotter overall. This also led to strong, strange weather patterns, possibly including powerful seasonal monsoons that brought heavy rain to the coast and left the inner land bone dry. But maybe the most fascinating part of Pangaea's story is how it affected life. Since all the land was connected, animals could wander freely across the entire supercontinent. Creatures that once lived together on Pangaea now have fossil remains scattered across continents that are oceans apart. Take, for instance, the Mesosaurus, a small freshwater reptile. Fossils of this animal have been found in both South America and Africa, even though those continents are now separated by the Atlantic Ocean. Another example is the Lystrosaurus, a strange, pig-sized creature with both reptilian and mammalian features. Its bones have been discovered in places as far apart as Africa, India, and Antarctica. These clues are proof that the lands were once connected and that animals could roam without limits. The same thing happened with plants. One famous example is a prehistoric fern called Glossopteris. Fossils of this plant have been unearthed in South America, Africa, India, Australia, and Antarctica. These places today have wildly different climates, from steamy jungles to frozen tundra. But back when they were part of Pangaea, they shared similar ecosystems, which allowed this plant to grow almost everywhere. Pangaea also played a role in one of the most devastating moments in Earth's history, the Permian Triassic extinction, sometimes called the Great Dying. This happened about 252 million years ago. During this catastrophe, nearly 96% of all ocean life and about 70% of land-dwelling vertebrates went extinct. Scientists are still trying to figure out exactly why it happened. Some believe it was caused by huge volcanic eruptions in Siberia, while others think it had to do with the extreme climates of the supercontinent. Most likely it was a combination of both, and even after Pangaea broke apart, its influence continued. As the land masses drifted away from each other, new environments formed, new mountains, new coastlines, and new climates. Life had to adapt. New species evolved to fit into these changing worlds, leading to even greater diversity in plants and animals. In the end, Pangaea matters because it shaped so much of what we see around us today. The way the continents are arranged, where mountain ranges sit, where oceans flow, and even how animals and plants are spread across the globe, all of this traces back to Pangaea. It also reminds us that Earth is always changing. Pangaea wasn't the first supercontinent, and it won't be the last. Before Pangaea, there were others, like Rodinia and Columbia. In the far future, millions of years from now, the continents may come together again to form a brand new supercontinent. Studying Pangaea is like holding a time machine. It helps us understand not just the ancient past, but the living, moving nature of the planet we call home. It shows us how everything is connected, and how even the mightiest of continents are part of an endless, beautiful cycle of change. For most of human history, people believed that the continents, the vast landmasses we live on, were fixed in place, like permanent fixtures of the Earth. The very idea that whole continents could slowly drift across the planet seemed so strange and unbelievable that many experts laughed at it or rejected it completely. But what was once considered a wild and ridiculous thought is now one of the most important scientific ideas in all of geology. This idea is called plate tectonics, and it helps explain some of Earth's most powerful and mysterious forces, like earthquakes, volcanoes, huge mountain ranges, and even the way ancient animals and plants were spread across the globe. At its core, plate tectonics tells us that the Earth's outer layer, called the lithosphere, is not one solid shell. Instead, it is made up of several massive stiff plates that fit together like a giant jigsaw puzzle. These plates are always moving, although so slowly that we can't see it happen. They usually move only a few centimeters each year, about the same speed your fingernails grow. Some of these plates carry continents, while others make up the floors of the oceans. Where these plates meet, three main types of interactions occur. Divergent boundaries are where plates move apart. As they separate, hot molten rock from deep inside the Earth rises up to fill the gap and creates new crust. This is how the long underwater mountain chains called mid-ocean ridges are formed. Convergent boundaries are where plates crash into each other. When two continental plates collide, they can push up huge mountain ranges like the Himalayas. When an oceanic plate meets a continental plate, the oceanic plate often gets pushed down into the Earth's interior, forming deep ocean trenches and volcanic chains, and triggering massive earthquakes. Transform boundaries are where plates slide past one another. These sliding movements often cause stress to build up along cracks or fault lines, and when the stress is suddenly released, we get earthquakes. A famous example of this is the San Andreas Fault in California. What powers all this movement? Deep inside the Earth, the mantle, a layer of hot, thick rock is constantly in motion. You can imagine it like a giant pot of soup boiling on a stove. Heat from the Earth's core causes the hotter, lighter material to rise and the cooler, heavier material to sink. These slow, circular flows of heat and rock are called convection currents, and they gradually drag the tectonic plates above them. But this amazing theory didn't appear overnight. The journey to discovering it was long, difficult, and filled with doubt. It began with a bold German scientist named Alfred Wegener, who was born in the year 1880. Wegener was not a geologist by training. He studied the weather and explored polar regions, but his curious mind and sharp eyes noticed something incredible. Around the year 1912, Wegener introduced a daring new idea called continental drift. He noticed how well the coastlines of continents like South America and Africa seemed to fit together, almost like puzzle pieces. This made him wonder, could these continents have once been connected? Although others had noticed this curious fit before, Wegener was the first to collect and organize strong evidence from many scientific fields to support the idea that continents had actually moved. One piece of evidence came from fossils. He pointed out that fossils of a small freshwater reptile called Mesosaurus were found only in South America and Africa, even though this animal could never have swum across an ocean. This suggested those continents had once been joined. He also highlighted fossils of land animals like Lystrosaurus and Cynonathus, found on continents that are now thousands of kilometers apart, including Africa, India, and Antarctica. Perhaps most famously, he showed that fossils of an ancient fern called Glossopteris had been found across South America, Africa, India, Australia, and even Antarctica. This plant could not have floated across oceans. Its wide distribution only made sense if those continents had once been part of a single massive landmass. Wegener also looked at rocks and mountains. He found that mountain ranges like the Appalachians in eastern North America matched up almost perfectly with mountain ranges in Europe and North Africa, such as the Caledonian and Atlas Mountains. These ranges had similar rock types and ages, which suggested they had formed during the same ancient events, when the continents were still connected. He even used ancient climate clues to back up his theory. Wegener found evidence that glaciers had once covered parts of India, Africa, and Australia, places that are now far too warm for ice. This only made sense if those regions had once been near the South Pole. On the flip side, he discovered coal deposits, which form in hot, swampy environments, in places like Antarctica, which is now a frozen land. This showed that Antarctica must have once been located much closer to the equator. Even though Wegener's ideas were supported by a wide range of evidence, from fossils to rocks to climate, many scientists in his time did not believe him. The main reason? He could not explain how the continents moved. Wegener suggested that the continents somehow pushed their way through the ocean floor, or that Earth's spin and the pull of the moon might have dragged them along. But physicists showed that these forces were far too weak to move such massive pieces of land. Without a clear mechanism, many experts refused to accept his theory. Also, because Wegener was not a geologist, some in the scientific community saw him as an outsider and were reluctant to accept his ideas. So for many years, Wegener's theory remained controversial, a brilliant idea ahead of its time. It wasn't until the 1950s and 1960s that everything changed. A new scientific revolution began, and it gave scientists the missing clues that finally proved Wegener was right. One of the most important discoveries was seafloor spreading. Two scientists, Harry Hess from the United States and Robert Dietz from Canada, suggested that new ocean crust was constantly being formed at mid-ocean ridges. As molten rock came up from the mantle, it cooled and hardened, slowly pushing older crust away from the ridge like a conveyor belt. But the strongest proof came from the study of paleomagnetism, the ancient record of Earth's magnetic field. scientists found that iron minerals in the ocean floor lined up with Earth's magnetic field when the rock first formed. And since Earth's magnetic field flips every few 100,000 to few million years, the ocean floor had stripes of rock pointing in different directions: normal polarity, then reverse polarity, then normal again, and so on. These magnetic stripes were mirrored perfectly on both sides of the mid-ocean ridges, like a barcode. This showed that new crust was forming at the ridges and spreading outward in both directions. Later, drilling into the seafloor confirmed that the rock got older the farther it was from the ridge, just as seafloor spreading predicted. Alongside the discovery of seafloor spreading, modern science has brought us powerful new tools that offer clear and undeniable proof that the continents really are moving. One of the most important tools is the Global Positioning System, or GPS. This system uses a group of satellites that orbit high above the Earth. With this advanced technology, scientists can now measure the movement of Earth's giant tectonic plates with astonishing accuracy, down to just a few millimeters each year. By placing GPS receivers in different spots all over the world, on separate continents and even on individual islands, researchers are able to track how these locations slowly shift over time. These shifts happen very gradually, but they are constant and they add up. Thanks to this technology, scientists can see the continents drifting in real time, just as the theory of plate tectonics predicts. These precise measurements leave no room for doubt. They prove beyond question that the Earth's crust is indeed moving. Even the last few doubters, who once scoffed at the idea, have been silenced by the clear evidence from space. But GPS is not the only source of proof. Since the time of Alfred Wegener, who first suggested that continents drift, scientists have made incredible progress in studying rocks and mountains. Today, they can use advanced dating techniques to figure out the exact ages of rock layers. This allows them to match rock formations on one continent with identical formations on another, often on the opposite side of an ocean. These matches support Wegener's old observations in ways he could never have imagined. Some mountain ranges on different continents show the same patterns of bending and breaking, huge folds and long cracks called faults, that were clearly caused when massive landmasses collided in the distant past. This tells us that those continents were once connected and later slammed into each other as they moved. On top of that, when scientists look at where the world's volcanoes and earthquakes happen, they find that these dramatic events are not scattered randomly. Instead, they cluster tightly along the edges of tectonic plates. This is exactly what we would expect if the plates are moving and bumping into each other. Even the bottom of the ocean tells part of the story. Deep-sea drilling missions have allowed scientists to bring up samples of the ocean floor. These samples show exactly how old the seafloor is and how it was formed, evidence that fits perfectly with what plate tectonic theory predicts. And there's more. Scientists now use a technique called seismic tomography. This method works by studying how earthquake waves travel through the Earth. It's like taking a giant X-ray of the planet. These 3D images have shown hot plumes of rock rising from deep inside the Earth and cooler, denser slabs of rock sinking down into the mantle. These features reveal how the Earth's interior moves and churns, what scientists call mantle convection. This deep movement of hot and cold rock is believed to be the engine that drives the slow, steady shifting of the tectonic plates above. The journey from Alfred Wegener's bold but ridiculed idea of continental drift in the early 20th century to the modern, widely accepted theory of plate tectonics is one of the most inspiring tales in the history of science. It shows how powerful evidence can eventually overcome doubt and opposition. It also reminds us of how important it is to look at problems from many angles, combining geology, physics, chemistry, and even space technology. Today, plate tectonics is no longer just a clever theory. It is the foundation of how we understand our planet's changing surface. It explains not only the history of Earth's continents, but also gives us clues about what will happen in the future. It is the very process that brought the ancient supercontinent Pangaea together more than 300 million years ago, and later tore it apart, shaping the land, the oceans, and even the evolution and spread of life on Earth. When we talk about Earth's deep and distant past, so far back that it stretches beyond anything we can witness today, one name almost always takes centre stage: Pangaea. This enormous land mass is the most famous of all supercontinents. It was the last time most of Earth's continents were joined together, and its eventual breakup set the stage for the modern map of the world that we now know. But if we really want to understand Pangaea, we must journey even farther back in time, long before it came together. That's because Pangaea was not the first supercontinent to exist, and it certainly won't be the last. In fact, Earth has gone through many cycles where its continents slowly came together into one giant landmass, only to split apart again over millions and millions of years. This repeating pattern is known as the supercontinent cycle, and it is driven by the slow, churning movement of the rocks deep beneath Earth's surface in what is called the mantle. This powerful cycle of forming and breaking apart supercontinents has been happening for billions of years. Each cycle leaves behind clues in the rocks, mountains, and magnetic patterns of the Earth's crust, clues that scientists study carefully to learn more about the planet's inner workings and its long and dramatic history. By studying supercontinents that existed before Pangaea, like Kenneland, Columbia, sometimes called Nuna, and Rodinia, scientists have been able to piece together an extraordinary story about how Earth has evolved, how its surface has changed, and how life has responded to these massive changes. Let's go way, way back, to a time so long ago that life on Earth was just beginning, and the air we breathe today had not yet formed. Our journey starts in a time called the Neo-Archean era, which lasted from about 2,700,000,000 to 2,500,000,000 years ago. This is when a supercontinent called Kenneland likely came together. It is one of the earliest known supercontinents for which scientists have strong geological evidence. Imagine a world so different from ours. The sun may have shone more dimly, the atmosphere may have had little or no oxygen, and life, if it existed, was simple and microscopic. But deep beneath the surface, the forces that drive continents, the movement of tectonic plates, were already at work. Kenneland wasn't formed by the coming together of the continents we know today. Instead, it was built from many smaller land pieces called proto-continents and ancient stable blocks of rock called cratons. These cratons are some of the oldest parts of today's continents. Some of the key cratons that made up Kenneland include the Baltic Shield, which is now part of Scandinavia and Eastern Europe, the Superior Craton in present-day North America, and the Yilgarn Craton in Western Australia. Scientists didn't find a single big chunk of land called Kenneland sitting out there somewhere. Instead, they figured it out by comparing very old rocks from different continents and noticing they once fit together. They used something called paleomagnetic data, a kind of ancient magnetic fingerprint locked in rocks, to show that these far-apart regions were once joined in a particular pattern. They also studied the ages of rocks, mountain belts, and matching mineral deposits found across these cratons. The formation of Kenneland was a major turning point in Earth's history. It marked a time when large areas of stable continental crust came together. Before that, Earth's crust was probably thinner, hotter, and more broken up, and tectonic activity may have been much faster. Kenneland shows us that even billions of years ago, the Earth had started to settle into a slower, more organised system of plate movement, a system more like the one we see today. But like every supercontinent, Kenneland's time eventually came to an end. Its breakup likely started around 2,500,000,000 years ago. Scientists think this breakup may have been caused by mantle plumes, giant columns of hot rock rising from deep inside Earth. These plumes would have pushed up on the bottom of the supercontinent, causing it to stretch, crack, and eventually tear apart. This process would have been accompanied by massive volcanic eruptions, spilling lava over huge areas and creating what are called large igneous provinces, or lipes. As Kenneland broke up, its cratons drifted away from each other, and new oceans began to form between them. This dramatic event helped scientists understand that the supercontinent cycle is not something recent. It is a process that has been happening for most of Earth's long history. Kenneland gave us a glimpse into how early continental crust formed and stabilized. It also helped us understand that huge volcanic events like ellipse can play a key role in breaking continents apart, a pattern we still observe in later supercontinent breakups. Now, let's move forward in time to the Paleo-Proterozoic era, which lasted from around 1,800,000,000 to 1,500,000,000 years ago. After Kenneland broke apart, The pieces didn't just float around forever. Over hundreds of millions of years, they slowly came back together, this time forming a new, even larger supercontinent called Columbia, which is also sometimes called Nuna. Columbia was much bigger and more complex than Canorland. It was formed through the collisions of many older cratons and newly formed land pieces. Imagine land masses the size of entire modern continents slowly crashing into each other. The force of these collisions pushed up enormous mountain ranges, some possibly larger than anything we see today. Key pieces of Columbia included Laurentia, which later became the core of North America, Baltica, parts of Scandinavia and Eastern Europe, Siberia, North China, West Africa, and parts of Australia. The evidence for Columbia is even stronger than for Canorland. Geologists have found wide belts of ancient mountains, called orogenic belts, that formed when these pieces collided. One major example is the Trans-Hudson Orogen, a huge area of deformed rocks that stretches across central Canada and the northern United States. In addition to these collision zones, scientists also found signs of anorogenic magmatism, igneous activity that happened without mountain building, often during the quiet periods after continents had already joined together. Columbia didn't last forever either. Its breakup began around 1,500,000,000 years ago. Just like before, it likely broke apart slowly through rifting events, where cracks in the crust opened up and new ocean basins formed. Columbia's story is incredibly important for understanding how Earth's tectonic system evolved. It shows us that plate tectonics was becoming stronger and more similar to the processes we observe today. The formation and breakup of Columbia also had effects far beyond just rocks and mountains. The Great Oxidation Event, when oxygen levels in Earth's atmosphere began to rise significantly, happened before Columbia formed. But Columbia's later history may have influenced how nutrients move through the oceans, possibly helping early complex cells known as eukaryotes begin to diversify. Interestingly, the time when Columbia existed is sometimes called the Boring Billion, a time when not much seemed to happen in terms of new life forms appearing. But this long period of tectonic calm actually shows how the stability of a supercontinent can affect the evolution of life itself. Our next destination on this incredible journey through Earth's deep past takes us to a time long before the age of dinosaurs, far back into the Neo-Proterozoic era, which lasted from around 1,100,000,000 years ago to about 750 million years ago. This is when an ancient supercontinent named Rodinia came into being. If Pangea is the superstar of Earth's continental history, known by almost everyone, then Rodinia is like its mysterious and powerful older sibling. While Rodinia might not be as famous, its story is just as dramatic, perhaps even more so. That's because when Rodinia broke apart, it kicked off some of the most extreme climate events in Earth's history, including a time when the entire planet may have been covered in ice, an event scientists call Snowball Earth. And not long after that, the first large, complex life forms began to appear. The name Rodinia comes from a Russian word meaning homeland, and it truly was an enormous landmass. It was most likely centered around what is now Laurentia, a geological core that would eventually become North America. But Rodinia was not built overnight. Its formation took place over millions of years and was driven by a massive mountain building episode known as the Grenville orogeny. This global event happened between 1,300,000,000 and 1 billion years ago. During this time, several ancient landmasses, including parts of what are now South America, Africa, Australia, India, and Antarctica, slowly drifted together and collided, sticking tightly around Laurentia. These collisions crumpled up the Earth's crust and created towering mountain ranges. Although these mountains have long since worn down, the deep rocky roots of these ranges can still be found today on multiple continents, proving that they were once part of a single united land. How do we know Rodinia ever existed? Geologists have gathered clues from many places. Paleomagnetic data, which tells us where rocks were on the globe when they formed, and similarities in rock types and structures across different continents provide strong evidence. For example, rocks from the Grenville era found in the eastern part of North America match up with rocks found in places as far away as Scandinavia, the British Isles, and even Antarctica. All these signs point to the fact that these lands were once connected as part of Rodinia. Rodinia's story doesn't end with its creation. Its breakup, which began around 750 million years ago and unfolded over the next couple of 100 million years, was just as important and far more explosive. Scientists believe that mantle plumes, huge columns of superheated rock rising from deep within the Earth, may have swelled beneath Rodinia. It created new coastlines and shallow seas. These exposed areas began to erode quickly, pulling carbon dioxide, a greenhouse gas, out of the atmosphere through chemical weathering. With less carbon dioxide to trap heat, Earth's climate cooled drastically. At the same time, volcanic activity linked to the breakup may have added heat early on, but it wasn't enough to stop the eventual deep freeze. The result? Ice may have covered almost the entire planet's surface. Yet from this icy catastrophe came new beginnings. Scientists believe that the environmental stress of these frozen times may have forced life to evolve in new, more complex ways. Soon after, the first large multicellular organisms, called the Ediacaran biota, appeared. This evolutionary leap laid the foundation for the Cambrian explosion, a time of incredible biological diversity that came next. Rodinia, therefore, didn't just change Earth's appearance, it changed the course of life itself. But Rodinia was not alone in shaping Earth's story. It followed two earlier supercontinents, Canorland and Columbia. These three are chapters in a much larger tale known as the supercontinent cycle. This is the idea that the continents are not fixed in place forever, but slowly come together to form massive land masses and then break apart again, in a repeating rhythm that takes 300 million to 500 million years per cycle. It's a timescale so huge it's hard to imagine, yet it is a fundamental part of how our planet works. There are two main ideas about how these supercontinents form. One is the introversion model, where a new supercontinent forms by closing up the internal oceans left behind from the previous breakup. The other is the extroversion model, where the land masses circle all the way around and meet on the far side by closing outer oceans. No matter the model, the pattern is the same. Land comes together, heat builds up beneath, and eventually the land tears apart once more, sending fragments drifting until they collide again and begin the cycle anew. This cycle affects far more than just the shape of continents. It plays a massive role in controlling Earth's climate, sea levels, ocean currents, and even the evolution of life. When all the continents come together, the inside parts of the supercontinent often become dry and hot because they are far from the oceans. Ocean currents get blocked or rerouted, and warm water doesn't flow the same way around the globe. This can cause big climate changes. The brightness, or albedo, of the Earth's surface also changes depending on how much ice and land there is, which can affect how much sunlight gets reflected or absorbed. The supercontinent cycle also affects the carbon cycle. When supercontinents break up, volcanoes become more active, pumping carbon dioxide into the atmosphere and possibly warming the planet. But at the same time, new land gets exposed to weathering, which pulls carbon dioxide out again, leading to cooling, as happened during Snowball Earth. Sea levels rise when the continents spread out because underwater mountain ridges grow and displace water. When the continents come back together, those ridges slow down and sea levels fall. Even evolution has danced to the rhythm of this cycle. When continents come together or pull apart, they create new environments and destroy old ones. This can lead to mass extinctions, but also evolutionary bursts. New shallow seas created by rifting offer ideal homes for sea life to thrive and diversify, just as we saw after Rodinia broke apart. The cycle also helps explain where we find valuable mineral resources today. Many important ores were formed either when continents collided under crushing pressure or when magma rose during rifting events. In the grand timeline of Earth, each of these ancient supercontinents has taught us something special. Canorland showed us the earliest beginnings of the cycle, a time when Earth's crust was still stabilizing. Columbia revealed how these events were becoming larger and more complex, laying the groundwork for more modern plate tectonics. And Rodinia, perhaps the most dramatic of all, showed us how deep Earth forces can reshape the surface and even affect life itself. The story of Pangea, the giant supercontinent that once brought nearly all the Earth's land together into one enormous piece, is not just about rocks and tectonic plates. It's a thrilling chapter in the grand story of life on our planet. Pangea's creation wasn't a quick or simple event. It was the dramatic result of a long, slow journey that lasted hundreds of millions of years. To truly understand how this mighty landmass came into being, we need to travel back to a much earlier time, a time known as the Paleozoic era. The Paleozoic era began around 541 million years ago and lasted until about 252 million years ago. Often called the Age of Ancient Life, this era was a time of breathtaking change. Life was rapidly evolving, climates were shifting wildly, and the continents were on the move, drifting, colliding, and reshaping the face of the Earth. It was a time when scattered chunks of land slowly came together in a massive slow-motion dance, eventually crashing into each other to form the mighty Pangaea. During this time, life made bold leaps, from simple sea creatures to complex plants and animals that conquered the land. Towering forests grew, strange marine creatures thrived, and reptiles began their climb to dominance, all while Earth's continents crept across the globe like pieces of an enormous puzzle. At the beginning of this era, the Earth's surface looked very different. The continents were broken into many smaller pieces, the leftover fragments of a much older supercontinent called Rodinia, which had already broken apart. But two massive landmasses were starting to stand out, and would play leading roles in the shaping of Earth's geography: Gondwana and Laurasia. Gondwana was already a well-formed supercontinent by the start of the Paleozoic. It wasn't newly created during this era. Instead, it had come together earlier, during the Neo-Proterozoic era, from pieces left over from Rodinia. Gondwana was massive, and for most of the Paleozoic it was the largest landmass on Earth. This enormous continent included land that would one day become South America, Africa, Antarctica, Australia, India, Madagascar, the Arabian Peninsula, and even bits of Florida and southern China. At the dawn of the Paleozoic, around 541 million years ago, Gondwana sat mostly in the southern hemisphere, with large parts of it near the South Pole. Picture this great landmass slowly drifting northward over many millions of years, moving across the globe like a gigantic ship. This steady movement brought huge changes. As Gondwana travelled, different parts of it passed through different climate zones. During the Ordovician period and again in the Carboniferous period, Gondwana went through long periods of glaciation, where large areas were covered in ice. Scientists know this because they've found deep scratches left by glaciers, called glacial striations, in places like India and Africa, which are warm today. These icy fingerprints are strong evidence of Gondwana's ancient journey near the pole. As Gondwana moved into warmer regions, its vast interior became increasingly dry and desert-like. But its edges, coastal areas and milder zones, were home to rich and thriving ecosystems. One of the most important pieces of evidence we have for Gondwana's past comes from plants. A special type of plant called Glossopteris grew widely across Gondwana, and fossils of it have been found on multiple continents, proving they were once joined together. Gondwana didn't just influence life, it also changed ocean currents and wind patterns, shaping global climates and helping determine where rain would fall and which regions would dry out. While Gondwana dominated the south, the northern hemisphere during the early Paleozoic was more like a jigsaw puzzle made of smaller pieces. These included continents like Laurentia, which would become most of North America and Greenland, Baltica, now Scandinavia and parts of Eastern Europe, Siberia, and Avalonia, which included parts of eastern North America, Britain and Ireland. Unlike Gondwana, which was already large and united, these northern pieces were scattered and drifting on their own paths. Over time, these northern land fragments slowly began to collide and merge, eventually forming another great landmass, Laurasia. This process happened later in the Paleozoic era and involved dramatic geological events, massive continental collisions that changed the Earth forever. As these continents came together, they experienced a variety of climates and gave rise to unique plants and animals, separate from those found on Gondwana. These biological differences highlight how isolated these continents were, until the eventual formation of Pangaea allowed species from north and south to mingle. The entire Paleozoic era can be seen as a giant slow-motion dance, with the continents acting as enormous dancers moving steadily toward a grand finale. That finale was the formation of Pangaea, and it wasn't the result of a single crash. It happened through a series of spectacular collisions. One of the earliest major collisions was called the Caledonian orogeny, which took place mostly during the Silurian and Devonian periods from around 440 million to 390 million years ago. This event saw Laurentia, Baltica and Avalonia slowly coming together. Between them was an ancient ocean known as the Iapetus Ocean, which gradually closed as the continents approached. When these land masses finally collided, they pushed up huge mountain ranges. Even today, we can see the remnants of these ancient mountains in places like the Appalachians in eastern North America, the Scottish Highlands, the Scandinavian mountains, and parts of Greenland. This union created a new northern supercontinent often called Euramerica or Laurasia. A key part of the Caledonian event was the Acadian orogeny during the Devonian period, when Avalonia collided more directly with Laurentia, helping to build even more mountains and solidifying the northern continents into a more united mass. The final and most dramatic collision came during the Carboniferous and Permian periods, between about 320 million and 250 million years ago. This was the moment when Gondwana and Laurasia, the two giants, finally came together in a global-scale event. Two massive mountain-building episodes marked this period: the Alleghanian orogeny and the Variscan, also known as the Hercynian orogeny. The Alleghanian orogeny was the colossal impact between Africa, part of Gondwana, and eastern North America, part of Laurasia. This mighty collision gave the final uplift to the Appalachian Mountains, shaping them into the rugged range we still see today. At the same time, on the other side of the forming supercontinent, the Variscan orogeny occurred as Africa and smaller land fragments collided with parts of Europe. This gave rise to mountain ranges across Central and Southern Europe, including the early forms of the Alps, Pyrenees, and Urals. These monumental collisions did more than just create mountains. They reshaped Earth's crust, caused intense volcanic activity, and changed the very structure of the planet. All of these events, stacked one upon the other like layers of a great geological cake, finally brought together every major landmass on Earth into one gigantic continent, Pangaea. This supercontinent stretched from the North Pole to the South Pole and was surrounded by a vast global ocean called Panthalassa. As Earth's continents slowly drifted and came together over hundreds of millions of years, life on our planet was also undergoing some of the most dramatic and awe-inspiring changes in its entire history. This grand chapter is called the Paleozoic era, and it spanned from about 541 million to 252 million years ago. It wasn't just a time of shifting land masses, it was a time when life exploded, evolved, crawled onto land, and faced some of the most devastating extinctions ever known. We begin with the Cambrian period, around 541 million years ago, where something extraordinary happened, the Cambrian explosion. During this time, the seas were bursting with new forms of life. Almost all the major groups of animals we know today, like those with backbones, shells and legs, appeared in the fossil record within a geologically short window of time. This burst of life didn't happen on land yet. Instead, it thrived in shallow oceans, especially along newly exposed continental shelves created by the breakup of an earlier supercontinent called Rodinia. These shallow marine areas were rich in nutrients, making them perfect nurseries for life to flourish. Then came the Ordovician period, stretching from about 485 million to 443 million years ago. Life in the oceans kept diversifying. This was when the first vertebrates, very early types of fish, appeared, and something even more incredible happened toward the end of this period. Plants began creeping onto land. These were simple, non-vascular plants, but their arrival marked a turning point in Earth's story. However, this period ended in disaster, one of Earth's first mass extinctions. Scientists believe it may have been caused by the vast southern continent Gondwana drifting over the South Pole. This shift triggered an ice age, glaciers grew, sea levels dropped, and many marine species vanished. Next came the Silurian period, from around 443 million to 490 million years ago. The seas were still bustling with life, and now we see the appearance of jawed fish, a major leap in evolution. Meanwhile, plants continued their march across the land. They developed vascular systems to carry water and nutrients, allowing them to grow taller. And it wasn't just plants. Early land animals appeared too. Tiny creatures like millipedes and scorpions began scuttling across the damp ground. As continents moved, they shifted ocean currents and created new habitats that kept pushing evolution forward. Then came the Devonian period, lasting from 419 million to 359 million years ago. This period is often called the Age of Fish, because so many new kinds of fish evolved. Some were armoured, some had jaws, and others began developing the ability to breathe air. The biggest breakthrough of all? The very first amphibians, vertebrates that left the water and ventured onto land. This was the beginning of a life's conquest of dry land. At the same time, the first forests started to appear, filled with tall, tree-like plants. These forests changed the land forever by stabilizing soil, producing oxygen, and laying the groundwork for future ecosystems. Once again, the slow but steady movement of continents helped shape these changes by altering coastlines, climates, and habitats. After that came the Carboniferous period, from about 359 million to 299 million years ago. This was a time when Earth turned green in a big way. Massive swampy forests spread across much of the northern continents, especially in a landmass called Laurasia. These forests were so vast and lush that when the trees died and were buried over time, they eventually turned into the coal we still use today. Amphibians grew more diverse, and for the first time, reptiles appeared, creatures that could lay eggs on land, allowing them to live farther from water. It was a major evolutionary leap. During this period, two large continents, Laurentia and Baltica, crashed into each other, forming a new northern supercontinent called Euramerica, or Laurasia. This collision changed the climate and helped create the swampy, oxygen-rich environments where life flourished. Oxygen levels in the air peaked during this time, and some insects like dragonflies grew to enormous sizes because of it. Now, we arrive at the Permian period, from 299 million to 252 million years ago. This was the final act of the Paleozoic era, and it was both triumphant and tragic. By this time, the mighty supercontinent Pangaea had fully formed, bringing together almost all the land on Earth into one giant mass. Reptiles spread across this vast land, adapting to its many different climates and landscapes. But this unification came with consequences. Because the landmass was so large, the inner regions became extremely dry. Ocean circulation changed, mountains rose, and the climate became more extreme and less stable. These changes set the stage for the greatest extinction event in Earth's history, the Permian Triassic extinction, also known as the Great Dying. Around 90% of marine species and 70% of land vertebrates were wiped out. One leading theory blames massive volcanic eruptions in Siberia, called the Siberian traps, for spewing out enormous amounts of greenhouse gases. These gases caused global warming, poisoned the oceans, and destroyed ecosystems across the planet. Some scientists also believe that the formation of Pangaea itself may have disrupted the planet's internal dynamics in ways that added to the catastrophe. Throughout the entire Paleozoic era, Earth's environment was in constant motion, literally and figuratively. The climate shifted between warm and icy periods, especially during the Ordovician and Carboniferous, when glaciers formed and sea levels dropped. As plants spread, especially during the Carboniferous, they pumped more and more oxygen into the atmosphere. This not only supported new life, but also helped some creatures grow to impressive sizes. In the oceans, the slow drifting and crashing of continents changed how water moved, how nutrients were spread, and which life forms could thrive. However, the Paleozoic era wasn't just a warm-up to the age of dinosaurs or a distant prelude to modern life. It was a time of dramatic transformation. It was during these hundreds of millions of years that life made its boldest moves, from tiny marine creatures to land-dwelling animals and towering forests. The Earth's crust shifted like pieces of a puzzle, guided by slow but powerful currents deep within the mantle. The continents Gondwana and Laurasia moved ever closer, locked in a slow-motion collision that finally brought about Pangaea, a supercontinent that reshaped the face of the world. Imagine the surface of the Earth not as a solid, unchanging shell, but more like an enormous living puzzle. Each piece of this puzzle is always on the move, slowly, quietly, but constantly shifting. This idea forms the core of what we now call plate tectonics, a groundbreaking concept that completely changed the way we understand our planet. The outermost layer of the Earth, known as the lithosphere, is broken into several gigantic sections called tectonic plates. These plates move over a softer, almost fluid layer underneath called the mantle. Even though their movement is incredibly slow, only a few inches every year, it is this gentle, patient drifting that creates some of Earth's most powerful and dramatic features. These moving plates can pull apart from each other, at what scientists call divergent boundaries, slide sideways past one another, transform boundaries, or, most powerfully of all, crash together, convergent boundaries. The most awe-inspiring of these interactions happen when two massive continental plates slam into each other. These are not small bumps or shoves. We're talking about planet-shaping collisions that unfold over tens of millions of years. They are the geological titans responsible for building the tallest mountain ranges on Earth, leaving behind mighty scars that tell the stories of ancient supercontinents like Pangea. When continents collide, it's not a gentle process. It's more like trying to push two enormous corks into a bucket of water. They both float and resist being pushed downward. Oceanic crust, being denser and thinner, usually sinks into the mantle when it meets another plate. But continental crust is thick and buoyant, and it refuses to go down without a fight. So instead of sinking, the rocks between the colliding continents begin to crumple, bend, and break, piling up into towering mountains. It's like shoving a rug from both ends. The fabric buckles and folds. Geologists have a name for this process, orogeny, which means mountain making. These mountains are not just surface features. Beneath them lies a deep, thickened foundation of crust that reaches far down into the Earth, like a buried root or a keel on a ship. This deep root helps support the mountain's weight and plays a role in isostasy, the way mountains slowly rise or sink over time, as erosion wears them down or glaciers melt and shift weight around. One of the most famous examples of a mountain range born from the birth of Pangea is the Appalachian Mountains in what is now the eastern part of North America. Today, the Appalachians are soft, rolling hills compared to the spiky, towering Himalayas. But don't let their appearance fool you. These gentle slopes once belonged to a truly gigantic mountain range, one that may have stood as tall as the Himalayas themselves. The Appalachians were not built in one moment, but over a series of massive continental crashes that took place over hundreds of millions of years. The final and most important of these collisions happened during a period called the Alleghenian orogeny, which occurred roughly between 320 million and 280 million years ago. This event was triggered when the continent known as Laurasia, an ancient version of North America, smashed into Gondwana, the huge southern supercontinent that included what is now Africa. But this wasn't the first time the area experienced powerful geologic events. Before the Alleghenian collision, the region had already been shaped by earlier mountain-building episodes, such as the Taconic and Akkadian orogenies. These earlier events were tied to the closing of an ancient ocean called the Ocean and the collision of small volcanic islands and microcontinents with Laurasia. These early crashes laid the groundwork, but the Alleghenian orogeny was the final thunderous blow that brought the full force of continental collision. During this colossal clash, the already existing layers of rock were folded, cracked, and shoved westward. Giant slabs of rock, some of them tens of miles thick, were thrust sideways over others for hundreds of miles, creating what geologists call a fold and thrust belt. This is exactly what formed the Appalachian Range. A feature known as the Allegheny Front marks the outermost edge of this dramatic deformation, a visible boundary where the Earth's crust was violently rearranged. The sheer scale of the Alleghenian orogeny is almost impossible to imagine. Experts believe that the ancient Appalachians might have soared as high as 25,000 or even 30,000 feet, rivaling today's Himalayas. This mountain chain once stretched for thousands of miles, acting as the central spine of the newly formed supercontinent, Pangaea. Even though hundreds of millions of years of wind, water, and ice have eroded these towering peaks, their bones still remain. The parallel ridges and deep valleys of the central and southern Appalachians show the remnants of those vast folds and thrusts, and deep inside the mountains we find metamorphic rocks like schist, slate, and gneiss, rocks that were baked and squeezed under intense heat and pressure during the mountain building process. Huge piles of eroded sediment, sandstones, shales, and conglomerates lie in nearby basins to the west, forming what geologists call foreland basins. These thick layers of sediment are the washed-down remains of the once majestic peaks. Now, if we turn our eyes across the Atlantic Ocean to Russia, we find another mountain range that tells a similar story: the Ural Mountains. These rugged peaks stretch over 1,500 miles from the Arctic Ocean in the north to the Ural River in the south. Like the Appalachians, the Urals are the result of a massive continental collision that took place during the creation of Pangaea, between 320 million and 250 million years ago. The Urals formed when a landmass called Baltica, which would become part of Europe, collided with the Siberian continent and a smaller fragment called the Kazakhstan block. These once separate continents were divided by a narrow stretch of ocean called the Euralian Ocean. As the ocean floor was slowly pulled under and destroyed through subduction, the continents finally crashed together, creating the mountain chain. Much like the Appalachians, the Urals are built of bent and broken layers of sedimentary igneous and metamorphic rock. Their long, narrow shape reflects the tight zone where the collision occurred. However, the Urals have endured in a slightly different way. Unlike the humid climate of the Appalachian region, the Urals experience long periods of drier, more continental conditions, which help preserve some of their rougher features, even though erosion has worn them down too over time. Together, the Appalachians and the Urals stand as ancient monuments to the tremendous slow-moving power of plate tectonics. They are living records of Earth's history, silent storytellers of when whole continents danced across the globe, collided, and rose to the heavens. The Ural Mountains, which stretch from the icy Arctic Ocean in the north to the steppes of Kazakhstan in the south, are far more than just a geographical border between Europe and Asia. These ancient mountains tell a powerful and dramatic story about Earth's deep past, a tale written in stone. When we look closely at their rocks, we find clear signs that the Urals were born from a mighty collision between massive chunks of Earth's crust, much like two enormous ships crashing into each other and crumpling on impact. One of the strongest clues lies in the discovery of ophiolites within the range. These are slices of the ocean floor and the rocky mantle below it, which were somehow lifted up and thrust onto dry land. How did this happen? It could only have occurred during a colossal tectonic collision, when an ancient ocean was squeezed shut and its seafloor was crumpled up and pushed onto a continent. This proves that, millions upon millions of years ago, a vast ocean once existed where the Urals now stand. But the Urals are not just geologically fascinating, they're also incredibly rich in treasures. Deep beneath their peaks lie shimmering veins of gold, glittering specks of platinum, sturdy base metals like copper and nickel, and even beautiful gemstones. These mineral riches didn't just appear by chance, they were formed through intense geological activity triggered by the mountain building process. As the tectonic plates crashed into each other, they generated tremendous heat and pressure. Hot, mineral-rich fluids, called hydrothermal fluids, flowed through cracks in the rocks, carrying metals with them and depositing them in concentrated pockets. These conditions were perfect for forming valuable resources, which is why the Urals have long been known as one of the richest mineral belts on Earth. In a deeper sense, the Urals are like a scar on the surface of the planet, a visible reminder of where two once separate pieces of Earth were stitched together. They mark the line where a part of ancient Asia collided with a part of ancient Europe, joining together to form the eastern edge of a vast landmass known as Laurasia. Laurasia itself later became a key part of the supercontinent Pangaea, which united almost all the land on Earth into a single gigantic world. But the Urals are only one part of this mighty story. Across the globe, other mountain ranges also rose during the formation of Pangaea, each one a product of powerful collisions. Take the Appalachian Mountains in North America, for example. Though now worn down by time, they once stood tall, formed during the same era of tectonic upheaval. Another important mountain-building event, known as the Hercynian or Variscan orogeny, took place across what is now Europe. It formed a twisting, rugged chain that stretched from Spain and France, through Germany, and all the way to the Czech Republic. This massive belt of mountains was created when small land masses, called microcontinents, slammed into the southern edge of Laurasia, along with the larger continent of Gondwana. If we could rewind the clock and piece together the ancient puzzle of Pangea, we would see that these separate ranges, the Appalachians, the Hercynian belt, and even the Anti-Atlas Mountains of North Africa, were once part of a single, enormous mountain system. This vast chain, known as the Central Pangean Mountain Belt, stretched across the heart of the supercontinent like a rugged spine. It was one of the most dramatic features on the planet at the time. Towering peaks, high plateaus and long ridges rose up across thousands of kilometers, shaping wind patterns, blocking rainfall, and influencing the climate in ways that can still be traced today. The birth of Pangea was more than just a reshuffling of continents. It had enormous effects on Earth's entire environment. For one, it changed the climate. With such a massive continent covering so much of the planet's surface, many areas far from the oceans became dry and harsh. The middle of Pangea likely experienced very hot summers and freezing winters, extreme seasons caused by the lack of nearby water to moderate temperatures. These dry conditions led to the spread of deserts and salt flats, where huge layers of evaporate minerals formed over time. Meanwhile, close to the equator, things were very different. There, thick, steamy forests of towering trees and ferns thrived in swampy lowlands. Over millions of years, the dead plant matter from these swamp forests piled up and was buried, eventually turning into the thick coal beds that we mine today. These coal deposits are a direct legacy of the lush equatorial climate that existed during Pangea's time. Pangea also changed the oceans. As the continents came together, ancient seas were squeezed shut, and a single vast ocean, called Panthalassa, surrounded the land. This enormous ocean altered the way water moved around the planet. Ocean currents were redirected, which affected how heat and nutrients were spread across the globe. Marine life too had to adapt to this changing world, and new species rose while others faded away. The rise of the supercontinent also meant the rise of huge new mountains. As these mountains eroded over millions of years, rivers carried their sediments and dissolved minerals into the sea, changing the chemistry of the oceans and possibly influencing the evolution of marine organisms. At its core, the tale of Pangea is a story of awe-inspiring power, of tectonic plates, hundreds of kilometers thick, slowly crashing into each other over spans of time measured not in centuries but in hundreds of millions of years. The mighty mountains they created, like the Urals and the Appalachians, are more than just beautiful landscapes. They are the physical scars of Earth's ancient battles, proof of a world that is always in motion, always changing. Understanding these mountain-building events helps us understand not only Earth's surface, but also how the planet works deep inside. It shows us how something as slow and invisible as plate tectonics can create continents, shift oceans, build mountains, and even change the course of life itself. Pangea was not just a supercontinent. It was a turning point in Earth's history, shaping everything from weather and climate to evolution and extinction. However, the Earth is not a frozen, lifeless rock. It is a living, breathing world, its history carved into stone, its past still visible in the folds of mountain ranges, and its future still being written by the slow but unstoppable movements of the ground beneath our feet. The idea that all the continents we know today were once part of one gigantic landmass, called Pangea, is one of the most fascinating stories in Earth's history. Just imagine, North America, Africa, Asia, Europe, and all the rest, once locked together in a single, massive supercontinent. It sounds like something from a science fiction story, but it's a real scientific concept that continues to amaze people to this day. However, for this extraordinary idea to be taken seriously by scientists, it had to move beyond simple imagination. It had to be proven. Geologists, scientists who study the Earth's structure and history, needed solid, testable answers to big questions. When exactly did all the continents come together? And what kind of evidence do we have to show that Pangea truly existed? These answers didn't arrive overnight. In fact, they were slowly and carefully gathered over many decades. Like detectives solving an ancient mystery, scientists studied rocks, fossils, and clues from deep within the Earth. Piece by piece, they built a case. Today, most scientists agree that Pangaea came together completely around 335 million years ago, during a time known as the Carboniferous period. But this great union of continents didn't happen all at once. It was the result of millions of years of slow movement, continents drifting across the surface of the planet, crashing into one another and joining together through mighty geological collisions. This grand assembly formed a landmass so vast that it affected everything, from the Earth's climate to the plants and animals that lived there. To uncover when and how this happened, scientists had to study the Earth like forensic experts. They dug into rock layers, studied ancient fossils, and explored hidden patterns in the Earth's magnetic field. One of the most powerful pieces of evidence came from a field of study called paleomagnetism, the science of ancient magnetism locked inside rocks. Here's how it works. When certain rocks form, either from cooling lava or from sediment settling, they contain minerals that line up with Earth's magnetic field, like tiny compass needles frozen in time. By examining these rocks from different continents and different ages, scientists could see how the continents had moved over time. What they discovered was amazing. When they rearranged the continents into the shape of Pangaea, all the magnetic data lined up perfectly. The apparent movement of the magnetic pole, called the polar wander path, became consistent across the continents. This was strong proof that these continents were once joined together, sharing the same magnetic history. And there was even more proof hiding beneath the oceans. Scientists studying the ocean floor discovered long ridges where new crust was being formed. As molten rock rose and cooled, it recorded Earth's magnetic field, just like rocks on land. These patterns showed that the seafloor had been spreading for millions of years, pushing continents apart. This could only mean one thing. If the continents are moving away from each other now, they must have been closer, or even joined together in the distant past. But the magnetic clues weren't the only evidence. There were also physical signs on land, mountain ranges, rock layers, and landforms that matched up across oceans. One of the best examples comes from the Appalachian Mountains in eastern North America. When scientists placed the continents back together into the shape of Pangaea, these mountains connected perfectly with the Hercynian Mountains in Central and Southern Europe and the Anti-Atlas Mountains in Northwest Africa. All three were part of a continuous chain called the Central Pangean Mountain Belt. Not only did they line up in shape, but the rocks themselves, their types, layers, and the folding and faulting inside were nearly identical. It was like finding matching puzzle pieces, or seams in a garment that had been cut apart and stitched back together. Another powerful clue came from the study of ancient land cores called cratons. These are the oldest, most stable parts of continents. When scientists compared them, they found that the Canadian Shield in North America fit neatly with the Baltic Shield in Europe and the West African Craton. These ancient land cores matched like pieces from a global jigsaw puzzle. Even more compelling was the study of ancient glacial deposits. Scientists found signs of ancient glaciers, such as tealites, rocks made from glacier debris, striations, scratches left by moving ice, and U-shaped valleys, spread across continents that are now far apart: southern South America, South Africa, India, Australia, and Antarctica. At first, this didn't make sense. These continents are now in warm tropical areas where glaciers shouldn't form. But when scientists reassembled them into the southern part of Pangaea, called Gondwana, it became clear. All those places were once clustered around the South Pole, where ice sheets would have made perfect sense. This was one of the earliest and strongest pieces of evidence for the theory of continental drift. The rocks also told stories about ancient climates. During the Carboniferous period, when Pangaea was forming, massive swampy forests stretched across the equator. These forests left behind rich deposits of coal that we still mine today. These coal deposits are found in places like North America, Europe, and parts of Asia, continents now far apart. But when you place them back together in Pangaea, those coal-rich swamps all lie near the equator, where the warm, wet climate would have helped the plants grow. On the other hand, deserts and dry regions left behind evaporites, minerals like salt and gypsum, and red beds, iron-rich rocks that form in dry climates. These are found in the interior parts of where Pangaea would have been, exactly where you'd expect dry conditions in a giant landmass far from the ocean. The distribution of these climate-sensitive rocks only makes sense if the continents were once connected. And then there's the fossil evidence, some of the most dramatic and easy to understand clues. One of the most famous fossil finds is that of Glossopteris, a fern-like plant with large tongue-shaped leaves. It grew from seeds that were too heavy to travel far by wind or water. Yet fossils of Glossopteris have been found in South America, Africa, India, Australia, and Antarctica. The only logical explanation is that these continents were once connected, allowing this plant to spread naturally across them. There's simply no way those seeds could have crossed wide oceans. All of this evidence, magnetic, geological, climatic, and fossil, paints a vivid and convincing picture. Around 335 million years ago, during the lush, coal-rich Carboniferous period, the Earth's continents slowly came together to form the mighty supercontinent of Pangaea. This wasn't just a moment in geological time, it was a turning point in Earth's story, shaping everything from the mountains we see today to the ancient plants and animals that once roamed across a united world. One of the most fascinating pieces of fossil evidence supporting the idea that the continents were once connected comes from a small freshwater reptile called Mesosaurus. This creature was only about 3 feet long, roughly the size of a small dog, and lived only in freshwater rivers and lakes. Its skeleton was quite fragile, and because it couldn't survive in salty seawater, it would have been impossible for it to swim across a wide ocean like the Atlantic. And yet, fossils of Mesosaurus have been found in only 2 distant places on Earth, in the southern part of Africa and in the eastern part of South America. These regions are now separated by thousands of miles of ocean, but back in the distant past they must have been right next to each other. This limited fossil distribution is a powerful clue. It strongly suggests that these 2 continents were once joined together as part of a much larger landmass. In fact, it's some of the clearest evidence we have that supports the existence of the ancient supercontinent called Pangaea. Another strong clue comes from a land-dwelling reptile named Lystrosaurus. This plant-eating animal was about the size of a modern pig and lived during the late Permian and early Triassic periods, between about 252 million and 248 million years ago. Unlike Mesosaurus, Lystrosaurus didn't live in the water at all. It walked on land and had no ability to swim across oceans. Yet, fossils of Lystrosaurus have been discovered in 3 faraway places: Antarctica, India, and South Africa. The fact that the same type of land animal once lived on all 3 continents tells us something incredible. They must have once been connected. These lands were once part of a huge southern portion of Pangaea called Gondwana. The age of the Lystrosaurus fossils fits perfectly with the time geologists believe Pangaea was fully assembled, making this evidence even stronger. We also have the case of Synagnathus, another land reptile that was about the size of a dog. Like Lystrosaurus, it could not have swum across an ocean. Yet its fossils have been found in both South America and Africa. Once again, this tells us that these continents were once part of the same landmass. But it doesn't stop there. Scientists have found even more matching fossils of ancient amphibians, other reptiles, early mammals, and even similar plant types on continents that are now widely separated. Many of these animals lived only on land or in fresh water, so there's no way they could have crossed vast oceans. These shared fossils tell a clear and consistent story. Long ago, the continents were joined together in one enormous supercontinent. What makes this story so compelling is how all the different pieces of evidence fit together. It's not just the fossils. Scientists have also studied the direction of ancient magnetic fields trapped in rocks, called paleomagnetism, compared rock layers and mountain chains across continents, and looked at ancient climate patterns. All of these different studies point to the same conclusion. Pangaea was real. It came together around 335 million years ago, during a time when Earth's surface was being reshaped in dramatic ways. The formation of Pangaea was one of the most important events in Earth's long history. It caused massive mountain building as continents collided, changed the way air and water moved around the planet, and had a huge impact on the evolution of life. Plants and animals could move freely across the giant landmass, and new species evolved in response to these new environments. The fossil record gives us a window into that ancient world. It allows us to imagine a time when creatures like Lystrosaurus and Mesosaurus roamed freely across lands that are now oceans apart. This isn't just a dry scientific fact, it's a powerful reminder that our planet is always changing. The ground we stand on is part of a slow but unstoppable dance, with continents drifting, colliding and reshaping the Earth over millions of years. The full assembly of Pangaea around 335 million years ago marked a turning point in Earth's story. It set the stage for everything that came after, both the physical shape of the world and the story of life itself. It's a beautiful example of how the Earth is alive with motion and change, constantly writing and rewriting its own history. Imagine a world where travelling from one side of the land to the other didn't just mean crossing a few countries or mountains, but meant crossing an entire planet-sized stretch of land, where the idea of sailing across the sea from one continent to another didn't even make sense. Why? Because there was only one colossal landmass covering nearly the entire surface of the Earth. This was Pangaea, the last great supercontinent of ancient Earth, a mighty, unified mass of land that existed for tens of millions of years. At the very heart of this gigantic continent lay a region that was unlike anything we know today. It was a vast and intimidating interior, a land so far from the oceans that it became a world of extremes. These were Pangaea's inner deserts, huge, dry and unforgiving landscapes where the climate was not just harsh, but downright brutal. Without the softening effects of ocean winds or moist sea air, the heart of Pangaea became a place of searing heat, biting cold and relentless dryness. Now think about just how massive Pangaea really was. This was not like any continent we know today. It stretched from the icy poles in the north all the way to the frozen lands of the south. It was made up of nearly all the continental crust on Earth. In today's world, continents like Asia or Africa may be large, but they still have oceans nearby that help keep temperatures a bit more stable and bring in rain. But Pangaea didn't work like that. Its size made something called continentality, a climate effect caused by being far away from oceans, so extreme that it's almost impossible to imagine today. Any moist air that started out over the Great Panthalassic Ocean or the smaller Tethys Sea would have had to travel thousands of miles inland to reach the centre of Pangaea. But along the way, that air would lose most of its moisture. By the time it arrived, if it ever did, it would be dry and dusty. And making things even worse were the massive mountains that Pangaea formed when its once separated land masses crashed into each other. These mountain ranges were built during the slow-motion collision of Earth's tectonic plates. Picture the Appalachian Mountains in what is now North America, the Scottish Highlands, and the ancient Hercynian or Variscan mountains that once rose in parts of Europe and North Africa. Back then, many of these mountains may have reached heights as great, or even greater, than today's Himalayas. They weren't just tall, they were long, stretching for thousands of miles, acting like massive stone walls that blocked rain clouds from travelling further inland. Here's what happened. As moist winds from the ocean moved toward the centre of the continent, they were forced to rise over the mountains. As the air went up, it cooled down and dropped its moisture as rain or snow on the ocean-facing side of the mountains. This created small green and lush areas like oases, but on the far side the wind came down dry and hot, creating rain shadows, enormous dry zones where little to no rain ever fell. These rain shadows didn't just make the land dry, they helped build enormous bone-dry deserts that could stretch for thousands of miles. The deserts in the heart of Pangaea were unlike anything we see today. Imagine endless seas of red and golden sand dunes, whipped and sculpted by fierce winds. Some areas might have looked like the Sahara Desert or the Arabian Desert, but many times larger. The wind would constantly shift the sands, covering ancient landscapes and then uncovering them again as centuries passed. Other parts of this region were wide, rocky plains or high, flat plateaus where almost nothing grew. Sometimes rare rains might have formed shallow lakes or small inland seas, but the sun would quickly evaporate them, leaving behind glittering salt flats that stretched to the horizon. The land was often stained with shades of red and orange, caused by iron-rich rocks reacting with oxygen, a process that gave rise to the famous red beds, found in ancient rocks today. which geologists now recognise as evidence of long-lost deserts. The weather in the centre of Pangaea was just as extreme as the landscape. Without large bodies of water to soak up heat during the day and release it at night, temperatures swung wildly. Daytime brought scorching heat that could be deadly to most forms of life. But once the sun went down, the land cooled rapidly, and the nights could be freezing cold. This massive difference between daytime and nighttime temperatures happened almost every day, and with the seasons, things only got worse. The summers were boiling hot while the winters were icy and harsh. The air was thin, dry, and often filled with swirling dust from the unending winds. But the effects of Pangaea didn't stop at its centre. It changed the weather for the entire planet. With one huge landmass surrounded by a global ocean, the way air and water moved around the world was completely different from today. During the hot summer months, the land heated up faster than the ocean, creating a giant low-pressure zone that pulled in wet air from the sea. This created super monsoons, enormous seasonal wind systems far more powerful than any modern monsoon. Some coastal areas may have received heavy rainfall during these months, but the rain rarely reached the inner parts of Pangaea. By the time the clouds got close, they had already dropped their water, leaving the central desert dry as ever. In the winter, the opposite happened. The land cooled quickly, forming high-pressure zones that pushed cold, dry air outward, further drying up the continent. This constant push and pull of air, driven by Pangaea's massive size and unusual shape, created global weather systems that were chaotic and intense. It's hard to overstate how strange and extreme the weather on Earth must have been during this time. The interior of Pangaea was not just dry. It was a land of extremes, of deadly heat and bitter cold, of vast deserts and towering mountains, of dust storms and forgotten inland seas. Thanks to the rocks and fossils left behind, we now know that this ancient supercontinent shaped the Earth's climate in dramatic ways that left a deep mark on the history of our planet. The land of Pangaea was not just made up of tall, majestic mountains. It was a vast and varied landscape, a grand patchwork quilt of wide-open plains, towering plateaus, deep valleys, and shifting basins. While the enormous Appalachian-Variscan mountain belt stretched proudly across the northern and central parts of the supercontinent, many other dramatic features shaped its surface. Between the high mountain ranges lay great flat plains and low-lying basins, some dry and dusty, others possibly holding shallow seas or temporary lakes, especially during warmer times when global temperatures rose and the water cycle became more active. These large basins, depending on how high or low they sat and how close they were to sources of moisture, could have transformed with the seasons or across millions of years. Sometimes, during wetter periods, they might have filled with water, becoming inland seas or vast saltwater lakes. But more often, these basins were dry, sun-baked lands where sand was carried by strong winds, piling up in thick layers. Over time, minerals left behind by evaporating water formed salty crusts called evaporites, signs of ancient arid conditions. As the Permian period moved forward, this period lasted from about 299 million to 252 million years ago. Pangaea itself began to feel the first signs of stress that would, much later, cause it to split apart. The Earth's crust in some areas started to slowly stretch and thin, opening the very first cracks in the supercontinent. These early rift valleys formed long, low depressions that sometimes collected water, creating narrow lakes or seasonal rivers. In places where these rifts formed deep enough, volcanic activity could occur as magma rose to the surface, especially within the interior of the landmass. Most of the major volcanoes, however, remained at the edges of Pangaea, near the zones where oceanic crust was sliding beneath continental crust, in a process called subduction. The river systems of Pangaea were nothing short of extraordinary. Because the continent was so enormous, stretching almost from pole to pole, it needed gigantic rivers to carry water across its surface. But many of these rivers never made it all the way to the ocean. Instead, they flowed into the dry heart of the continent and ended in inland basins where the water simply evaporated, leaving behind flat, dry lake beds called playas or glittering salt flats. The few rivers that did reach the great Panthalassic Ocean were truly massive. draining huge parts of the continent and flowing across vast distances. Unlike today's Earth, with many small continents surrounded by oceans, Pangaea had only a few places where rainwater could flow out to sea. This made its entire water system different, and even the chemistry of the oceans was affected by the weathering and erosion taking place deep in the dry interior. When we zoom out and look at Pangaea's climate during the Permian period, we find a world that was both strange and extreme. The amount of carbon dioxide in the air was much higher than it is today, which helped keep the Earth warm overall. But that warmth wasn't shared evenly across the globe. Because Pangaea was so huge, it didn't heat up or cool down quickly. It had something scientists call thermal inertia, a kind of climate sluggishness. That meant there were big differences in temperature between the hot equator and the cold poles, and the seasons were very intense. Even though the poles were part of the same landmass, they likely still had long, freezing winters, maybe even with large sheets of seasonal ice. Still, compared to earlier times like the Carboniferous period, when the Earth was gripped by widespread glaciation, the Permian was mostly ice-free. Clues about these ancient climates come from the rocks and fossils scientists have found scattered across today's continents. For instance, coal beds, which form in warm, swampy environments, are only found in thin strips near the edges of what used to be Pangaea, suggesting that most of the interior was far too dry to support thick forests or wetland plants. On the other hand, layers of red rock and salt deposits are found in great abundance in the central and subtropical regions, marking the spread of deserts. In short, the climate of Pangaea was a land of dramatic contrasts. Deep inside the supercontinent, the ocean's cooling and warming effects were missing. This created enormous deserts, powerful wind systems, and rain shadows behind giant mountain chains. The land itself was so large that it shaped the winds and weather patterns across the globe. It was a place where life had to adapt to scorching summers, freezing winters, dry winds, and scarce water. Plants and animals had to be tough, clever, and well-suited to survive such harsh conditions. Today, when we study the rocks left behind from Pangaea, now scattered across different continents like puzzle pieces, we see the fingerprints of this ancient world. They tell us stories not only about the Earth's surface, but about how climate and land work together to shape the destiny of life. The tale of Pangaea is not just about old rocks and dry deserts. It is a powerful reminder of how the shape and size of a continent can shape the heartbeat of an entire planet. The Permian period was one of the most dramatic and transformative chapters in Earth's long history. It lasted from about 299 million years ago to around 252 million years ago. This era marked the time when the supercontinent Pangaea truly came together as one enormous landmass, reshaping the face of the Earth. With continents locked together like giant puzzle pieces, everything began to change, from the shape of the oceans to the movement of air and water, and most importantly to the life that walked, crawled, swam, and grew upon the land. The story of the Permian is filled with both triumph and tragedy. It was a time when life on Earth became more diverse and more adapted to changing environments, yet it ended with the most devastating mass extinction the planet has ever known, an event so powerful that it wiped out most species and cleared the stage for the age of dinosaurs. To truly understand the Permian, we need to explore the types of creatures and plants that lived during this time, and how the rise of Pangaea, with its massive connected lands, shaped the ecosystems they depended on. At the beginning of the Permian, life on land was still feeling the aftershocks of the Carboniferous period, which had been a time of endless swamps and giant insects. Those ancient coal swamps had been lush, wet, and teeming with early amphibians. But as Pangaea finished forming, the global climate grew drier, more extreme, and more seasonal. Rainforests shrank, deserts spread. Life had to adapt quickly, or it would vanish. In the early part of the Permian, especially along rivers and in humid coastal areas, some of the old swamp plants still hung on. Towering lycopods like Lepidodendron and Sigillaria stood like prehistoric trees, sphenopsids like calamites, which resembled giant horsetails, and many types of ferns filled the landscape. These plants thrived in wet soil and formed thick peat beds, which over millions of years turned into the coal we mine today. But the world was changing. As rainfall became less reliable and temperatures more extreme, these water-loving plants began to decline. In their place rose the gymnosperms, plants that could conquer the dry, harsh lands of Pangaea. These included conifers, cycads, and ginkgos. Gymnosperms had an evolutionary advantage. They reproduced with seeds rather than spores. Their seeds had tough outer coatings and stored food inside, helping them survive dry seasons and sprout when rains returned. Wind-blown pollen also meant they no longer needed standing water to reproduce. Their leaves were tough and waxy, reducing water loss, perfect for surviving in deserts and dry forests. One of the most important and widespread plants of the Permian was Glossopteris. It belonged to a group called seed ferns, which had features of both ferns and seed plants. Glossopteris had broad, tongue-shaped leaves and grew in thick forests across the southern part of Pangaea, a region known as Gondwana. These forests covered what we now call South America, Africa, India, Antarctica, and Australia. In fact, the presence of Glossopteris fossils on all these continents became a key piece of evidence for Alfred Wegener when he proposed the idea of continental drift, a theory that later helped scientists understand how Pangaea existed in the first place. Glossopteris forests played a huge role in the Permian ecosystems. They provided shelter, food, and nesting grounds for many animals, especially the plant-eaters who relied on their leaves and seeds. The animals of the Permian were just as fascinating and strange. This was the age when the synapsids ruled the land. These were not reptiles in the modern sense, and not yet mammals either, but a group that would one day give rise to mammals. That's why they're often called mammal-like reptiles. In the early Permian, a group called the Pelecosaurs were especially common. The most famous among them is Dimetrodon, known for the large sail on its back. That sail might have helped it warm up in the morning sun or cool down in the afternoon heat. Pelecosaurs came in many shapes and sizes, from big meat-eaters to small bug hunters. As time passed, the Pelecosaurs gave way to a more advanced group of synapsids called the therapsids. These creatures had more powerful jaws, sharper teeth, and better ways of moving on land. Some even had body shapes and behaviours that were surprisingly similar to modern mammals. One group of therapsids, the Dinocephalians, included some of the biggest animals of their time. Some were peaceful plant-eaters with thick skulls, like Asteminosuchus, which had strange horn-like bumps on its head. Others were fierce predators, like Ankylosaurus, built for hunting. Their fossils are found in places like South Africa and Russia, showing how widespread they were across Pangaea. Another major group were the Dicynodonts. These strange-looking tusked plant-eaters came in many sizes, from small burrowing creatures the size of a dog to giant grazers as big as a hippopotamus. They had beak-like mouths for cutting plants, and 2 tusks. The name Dicynodont means 2 dog teeth. One of the most successful members of this group was Lystrosaurus. Its fossils have been discovered on every continent of Gondwana, including Antarctica, proving just how connected the land was during this time. Their ability to dig and burrow likely helped them survive dry spells and hide from predators. And speaking of predators, the Gorgonopsians were the terror of the Permian. These saber-toothed hunters had long canine teeth and strong jaws made for tearing into prey. Creatures like Gorgonops and Inostransevia were the top carnivores in their ecosystems, often preying on the abundant Dicynodonts. While synapsids were the stars of the Permian, reptiles were starting to make their own mark. Large armoured reptiles like the Pariasaurs, such as Scutosaurus, walked the earth, looking like slow-moving tanks, somewhere between a turtle and an armadillo. Smaller reptiles like the quick-footed Procolophonids scurried across the underbrush. In the late Permian, the ancestors of dinosaurs and crocodiles, the Archosauromorphs, began to appear, although they were still small and relatively unimportant compared to the ruling therapsids. Amphibians were still around too, mostly in the wetter regions. Giant frog-like creatures called temnospondyls lived in rivers and lakes. The air buzzed with insects, cockroaches, dragonflies, and the earliest beetles flitted through the forests and deserts. The massive size and unity of Pangaea had a profound impact on all of these living things. Here's how. Climate extremes. With one giant landmass, winds and ocean currents changed dramatically. The centre of Pangaea became very dry and hot, while coastal areas were more humid. This created strong environmental pressures, forcing plants and animals to adapt to harsher conditions. No barriers. Animals and plants could travel much farther across land without hitting oceans. This meant that species like Lystrosaurus or Glossopteris could spread across huge areas, giving scientists today valuable clues about how the continents were once connected. Mass extinction. Sadly, at the end of the Permian, around 252 million years ago, a massive catastrophe struck. Whether caused by volcanic eruptions, climate collapse, or other factors, the event wiped out about 90% of all marine species and 70% of land species. It was the biggest extinction in Earth's history. But from that destruction came opportunity. In the silence left behind, new life would rise, and the next great chapter, the age of dinosaurs, was just over the horizon, when all the continents came together to form the mighty supercontinent called Pangaea. It set off a chain reaction that transformed life on Earth in dramatic and far-reaching ways. This great union of land, which lasted from around 299 million to 252 million years ago, didn't just reshape geography. It changed how animals lived, how plants spread, and even how species evolved. First, and perhaps most importantly, the creation of Pangaea led to the mixing and blending of life on land. With nearly all the Earth's land joined into one massive supercontinent, there were no vast oceans in the way to stop animals from moving, or plants from spreading. Species that were once isolated by seas could now travel across enormous distances. Animals could roam freely across the land, and wind and water could carry plant seeds far and wide. This meant that distinct regions stopped having their own unique species, a phenomenon scientists call reduced provincialism. Normally, when continents are separated, species evolve differently in each place. But with Pangaea, many areas had the same or very similar species living in them. A famous example is the fossil of the plant Glossopteris and the tusked herbivorous animal Lystrosaurus. Their remains have been found in what is today South America, Africa, Antarctica, and India, continents now separated by thousands of miles of ocean. This shows how freely life could spread across Pangaea. In many climate zones across the supercontinent, similar plants and animals filled similar roles, making the planet's ecosystems more alike than ever before. Pangaea was not only vast in size but also in climate diversity. Because it stretched from the northern to the southern parts of the globe, it created large and extreme climate zones. The middle of the continent, far from the sea, was dry, hot and desert-like. The coasts, however, might have had milder weather or strong seasonal rains from monsoons. Life had to adapt to survive in these tough and varied environments. Plants like gymnosperms, which could handle dry conditions thanks to their tough leaves and protective seeds, began to take over the dry interior. In contrast, the older water-loving plants, like those that once filled swampy coal forests, could only survive in wet coastal areas or deep rift valleys where water was still plentiful. Animals too had to change. Many of the Permian synapsids, ancestors of mammals, developed clever ways to deal with the dry conditions. Some may have dug burrows to escape the heat. Others may have changed their diets to find food that was harder to eat but more available. Because these climate zones stretched over such wide areas, the same adaptations could help species survive across huge parts of the supercontinent. The connected land of Pangaea became a superhighway for migration. Animals were no longer stuck on one continent or another. If their environment changed, if it got too dry, too cold, or too crowded, they could simply move to a better place. Some species likely travelled thousands of miles in search of food, shelter, or mates. This freedom helped animals escape harsh conditions and follow their preferred climates as they shifted over time. But it also meant more competition in some regions, as different species moved into the same areas. Predators could travel far to find prey, and prey animals had to stay on the move to avoid them. All of this added a new layer of complexity to life on land, as ecosystems became linked on a continental scale. Another side effect of Pangaea's unity was that it likely led to fewer new species being created through isolation. One of the main ways new species evolve is when groups get separated by oceans, mountains, or other big barriers, and then change in different ways over time. Scientists call this allopatric speciation. But with Pangaea, there were fewer of these natural barriers. Although there were rivers and mountain ranges, they weren't enough to keep populations apart for very long. As a result, species could stay connected over long distances and didn't get many chances to evolve separately. This may have led to lower global biodiversity, meaning fewer total kinds of species, compared to times when the continents were split apart. So even though many species were widespread, there might have been less variety overall. The Earth's ecosystems were more connected, but also more uniform. With such an enormous landmass available, land-based ecosystems exploded in size and complexity. The balance of life tilted away from the oceans and toward the continents. The Permian period saw a burst of innovation and new forms of life on land. One major group to rise during this time were the therapsids, sometimes called mammal-like reptiles. These creatures were early relatives of mammals, and they thrived in the dry seasonal landscapes of Pangea. Meanwhile, gymnosperms, cone-bearing plants like early relatives of pines and cycads, became dominant in the plant world. Together, they filled vast stretches of land with life, turning deserts and plains into active ecosystems. Although marine life remained rich, the centre of evolutionary action had clearly shifted to the continents, where new challenges and opportunities were shaping life in fresh ways. Ironically, the same connectedness that allowed species to spread also made them more vulnerable to massive disasters. Because so many ecosystems were linked, a single catastrophic event could impact the entire world. And that's exactly what happened at the end of the Permian period, about 252 million years ago. Huge volcanic eruptions in what is now Siberia, called the Siberian Traps, released enormous amounts of carbon dioxide into the atmosphere. This likely caused the Earth to warm drastically and made many regions too hot and dry for life. And because Pangaea was so uniform, with few hidden, isolated places to take refuge, species had nowhere to hide when the climate turned deadly. This helped cause the Permian Triassic extinction event, the most devastating extinction in Earth's history. Around 90% of all marine species and about 70% of land-dwelling vertebrates were wiped out. The story of life on Pangaea is one of incredible unity and great vulnerability. The joining of continents created a world where animals and plants could travel freely, where new types of land ecosystems rose to power, and where adaptations to dry, harsh conditions became key to survival. But this same connectedness meant that when disaster struck, it struck everywhere. Pangaea shows us how the movement of continents, the slow dance of tectonic plates, can reshape the world in both beautiful and terrible ways. The life that lived on this supercontinent was both a triumph of evolution and a victim of Earth's ever-changing nature. Imagine a time long when life on Earth came dangerously close to disappearing entirely. This wasn't just a local disaster, like a volcano erupting or a hurricane sweeping through a region. No, this was a full-scale planetary crisis, a mass extinction so vast that it wiped out nearly 90 out of every 100 species living in the ocean, and about 70 out of every 100 species of animals living on land. This terrifying moment in Earth's history happened around 252 million years ago, during a time scientists call the Permian Triassic extinction. But it also has a more chilling nickname, the Great Dying, and that name is no exaggeration. Out of all the extinction events that have ever happened in Earth's 4.5 billion year history, this one was the most devastating of all. It was as if life on Earth had to pass through a narrow doorway of survival. Many species couldn't make it through, and those that did would take millions of years to recover. But before we dive into this cataclysm, let's take a moment to understand what the world looked like just before everything fell apart. Back then, Earth looked nothing like it does today. All the continents were joined together into one giant landmass called Pangaea. This supercontinent stretched almost from the North Pole all the way to the South Pole. Because of this unique shape, the world's climate and ocean currents were very different from what we know today. The middle parts of Pangaea, far away from the oceans, were dry, harsh deserts. Rain was rare, and temperatures could swing wildly, but along the coasts the climate was a little more forgiving, sometimes even tropical, with rainy and dry seasons much like modern monsoons. Despite these challenges, life was thriving. The oceans were filled with an incredible variety of creatures, especially invertebrates like ammonoids, brachiopods, bryozoans, and colourful coral reefs. On land, a group of animals called synapsids, ancient relatives of mammals, dominated. Among them were the powerful gorgonopsids, fierce predators with saber-like teeth, and the more peaceful dicynodonts, plant-eating animals with beaks and tusks. One of the most common of these was Lystrosaurus, a stocky little herbivore that would become a surprising survivor of the coming apocalypse. The land was also covered with forests of conifers, cycads and ferns, forming green canopies that supported complex food chains. This world might not have looked as colourful or busy as today's Earth, but it was full of life, a planet pulsing with activity. And yet, deep within the Earth, powerful forces were waking up, forces that would soon bring unimaginable destruction. The most likely cause of this global disaster was a titanic series of volcanic eruptions in what is now Siberia, in northern Asia. This wasn't just one volcano going off. It was a massive region called the Siberian Traps, where lava poured from huge cracks in the ground, not for days, not for years, but possibly for as long as 1 million years. Imagine rivers of molten rock erupting from the Earth's crust, not in cone-shaped mountains, but in deep, gaping fissures stretching for hundreds of kilometers. These eruptions created enormous sheets of black basalt rock, some thousands of meters thick. Scientists believe that millions of cubic kilometers of lava spilled out during this time, enough to cover entire continents. But the lava wasn't the only problem. These eruptions also released gigantic amounts of gas into the atmosphere, especially carbon dioxide and sulfur dioxide. Sulfur dioxide can cool the planet by reflecting sunlight, but carbon dioxide traps heat. Over time, the warming effect won out, turning Earth into a hothouse. Worse still, the lava didn't erupt into clean, empty rock. It tore through underground layers filled with coal, oil, and salt deposits. This caused even more deadly gases to be released, like methane, a greenhouse gas even more powerful than carbon dioxide, and chemicals like chlorine and fluorine that could damage life in other ways. All of this combined to create an atmospheric disaster on a scale Earth had never seen before. At first, the massive release of sulfur may have triggered a short-term volcanic winter, cooling the planet for a brief time, but that didn't last. The steady and overwhelming release of carbon dioxide and methane caused temperatures to skyrocket. Over a relatively short time, in geological terms, global temperatures may have risen by more than 10 degrees Celsius. That's enough to turn forests into deserts and make the tropics nearly unlivable. This rapid warming gave plants and animals no time to adjust. Forests shriveled, rains stopped falling, and vast stretches of land became dry and cracked. Plants weakened and died. With them went the herbivores that fed on them, and soon after the predators that fed on the herbivores followed. The entire food web began to collapse. But perhaps the most horrifying changes happened in the oceans. As the water warmed, it could no longer hold as much oxygen, and oxygen is just as essential for sea creatures as it is for those on land. The warmer the oceans became, the more their oxygen levels dropped, creating what scientists call dead zones. On top of that, the massive amounts of carbon dioxide in the atmosphere were being absorbed by the oceans, making them more acidic. This made it nearly impossible for creatures like corals, shellfish, and plankton to build their shells and skeletons. Without these tiny but essential creatures, marine ecosystems began to collapse from the bottom up. As oxygen disappeared and acid levels rose, more and more marine life perished. The oceans, once teeming with vibrant and diverse communities, became hot, acidic, and nearly lifeless in many parts of the world. The Permian Triassic extinction, the Great Dying, left Earth scarred and silent. The forests were thin, the oceans were quiet. Life had not ended, but it had been nearly erased. It would take millions upon millions of years for the Earth's ecosystems to rebuild, and for new species to evolve and take over the empty niches left behind. But through this unimaginable catastrophe, life endured. Some species, like the tough little Lystrosaurus, managed to survive and spread across the continents. From the ashes of extinction, evolution would eventually give rise to the age of dinosaurs, and much later to our own story. Imagine the oceans of Earth turning into giant, lifeless pools of poison. One of the most terrifying changes during the greatest extinction in Earth's history, what scientists call the Great Dying, was what happened beneath the waves. As the planet heated up, the oxygen levels in the oceans began to drop. The surface waters, once full of life-giving oxygen, stopped mixing with the colder, deeper layers. The oceans became stratified, like a layered cake, with oxygen only at the top and none at the bottom. Without mixing, the deep ocean turned into a suffocating void. This deadly change didn't stay hidden in the deep. The anoxic zones, places completely without oxygen, began to rise. They crept upwards into shallower waters, turning thriving marine habitats into silent graveyards. Fish, coral, shellfish, and other ocean creatures that had once filled these waters began to die in enormous numbers. But the horror didn't end there. In these low-oxygen waters, strange bacteria that don't need oxygen to survive, called green sulfur bacteria, started to multiply. These microbes released a gas called hydrogen sulfide, a poisonous substance that smells like rotten eggs. As this toxic gas built up in the oceans, a new nightmare emerged: euxenia, a state where the water had no oxygen and was full of poisonous gas. The oceans were no longer just lifeless, they were toxic. Evidence of this nightmare is still found today in the rocks. Around the world, scientists have discovered layers of black shale, rich in organic matter and sulfur, marking the presence of these deadly, poisonous waters. It's like the Earth itself recorded the memory of a time when its oceans turned dark, smelled foul, and became deadly to nearly all life. The consequences were truly catastrophic. Tiny plankton, coral reefs, massive fish, and even top predators in the oceans died off. Some were poisoned by hydrogen sulfide, others simply suffocated. Even the thermocline, the invisible boundary that separates warm surface waters from cooler deep waters, moved upward. This shift dragged toxic, oxygen-starved waters close to the surface, turning previously safe habitats into death zones. Ocean ecosystems that had flourished for millions of years were destroyed almost overnight. And then, things got even worse. Scientists believe that hydrogen sulfide didn't just stay in the oceans. Some of it escaped into the atmosphere. This gas may have poisoned land animals and even damaged the ozone layer, the shield that protects life from dangerous ultraviolet rays. With the ozone weakened or gone, sunlight became deadly, burning plants and animals and possibly playing a role in mass death on land. This was a brutal chain reaction. Poisoned oceans harming the skies, and the skies raining more death back down on land. But this nightmare wasn't caused by a single event. It was a web of disasters, all feeding into one another. At the heart of it all were the Siberian traps, a vast region in what is now Russia, where, around 252 million years ago, enormous volcanic eruptions began. These eruptions poured out lava and gases for nearly 1 million years, releasing huge amounts of carbon dioxide into the atmosphere. The planet started to heat up, but it didn't stop there. As temperatures rose, methane clathrates, ice-like structures deep in the ocean floor and frozen ground, began to melt. These structures had trapped methane, a greenhouse gas much more powerful than carbon dioxide. As the methane was released, it caused even faster and more intense warming. It was like adding fuel to an already raging fire. Some scientists also believe that massive wildfires, sparked by dry conditions and changes in the atmosphere, may have added even more carbon into the air. Ocean currents changed, making it even harder for oxygen to circulate in the seas. Everything fed into everything else: warming oceans, deadly gases, suffocated life, poisoned skies. The Earth was locked in a deadly feedback loop. The result was a level of destruction Earth had never seen before, and hasn't seen since. About 90% of all marine species vanished. On land, about 70% of all vertebrate species, animals with backbones, disappeared. Ancient creatures that had survived for hundreds of millions of years were completely wiped out. The famous trilobites, which had existed since the Cambrian period, were finally gone forever. Blastoids, relatives of sea lilies, died out. Many types of brachiopods, crinoids, and ammonoids either vanished completely or were reduced to just a few surviving kinds. On land, giant predators like the gorgonopsids were wiped out. Only a few tough creatures like Lystrosaurus, a squat pig-sized reptile-like animal, managed to survive. Even among the once dominant synapsids, which would one day give rise to mammals, most were exterminated. The entire web of life collapsed. Scientists call it extinction selectivity. Some creatures could handle heat, low oxygen, or acidified waters, but most could not. Those that survived did so by luck, toughness, or unique adaptations. After the worst was over, Earth entered a period of deep silence. This was the early Triassic, a time sometimes called the dead zone. Life was reduced to a few hardy survivors. Most animals were small, this is known as the Lilliput effect, because large animals couldn't cope with the harsh conditions. The world was dominated by a few so-called disaster species like Lystrosaurus, which could survive where almost nothing else could. It took millions of years before life started to recover. But the world that eventually rose from the ashes was not the same. The extinction created ecological vacancies, empty roles in nature that would be filled by new, evolving species. This slow rebuilding process eventually led to the rise of the dinosaurs, and much later, the mammals. From the devastation of the Great Dying came the foundation for the modern world. Even today, scientists are still studying this incredible event. Using powerful tools, they analyze ancient rocks and sediments, looking for chemical clues. They track the timing of volcanic eruptions, shifts in climate, and oxygen levels in the oceans. They build complex models to simulate how everything might have happened. Although debates continue about the details, most experts agree that the Siberian Traps eruptions were the initial spark that lit the fuse for a global disaster. The Great Dying was not just the end of one era, it was a total reset of life on Earth. It is a chilling reminder of how connected our planet's systems are, and how quickly everything can fall apart when balance is lost. From the depths of poisoned oceans to the skies filled with deadly gas, the world of 252 million years ago faced a disaster so complete that it nearly erased life itself. But from that darkness, after a long and painful struggle, life began again, smaller, humbler, and ready to write a new chapter. Imagine a planet rising slowly from the ashes of the greatest biological catastrophe in its entire history. This was Earth at the dawn of the Triassic period, which began around 252 million years ago and ended about 201 million years ago. The world had just survived the Permian Triassic extinction, a mass die-off so intense that it wiped out nearly all life in the oceans and a huge number of species on land. The Triassic began in a world nearly emptied of life and ended with yet another extinction, less severe but still powerful enough to shake up life once more. In between those two extinction events, something incredible happened. Life came back, slowly, painfully, and in strange and unexpected forms. Earth's ecosystems started to rebuild themselves. This was a time of new beginnings, a biological reboot. Plants and animals began to experiment with new forms, filling up the empty ecological spaces left behind. It was during the Triassic that the very first dinosaurs appeared, along with the earliest ancestors of mammals, our own distant relatives. The stage was set for dramatic evolutionary changes, driven by opportunity, survival, and relentless competition. With so many species wiped out, the survivors found themselves in a world with fewer rivals and many open niches. Life, in essence, had room to grow and explore again. The Earth of the Triassic looked very different from today. Almost all of the land was clumped together into a single colossal supercontinent called Pangea. This massive landform stretched from pole to pole, surrounded by a vast global ocean called Pangaea. Because so much of the land was far from the ocean's cooling influence, the interior of Pangea was incredibly hot and dry. Deserts spanned large parts of the land, baking under an unforgiving sun. Still, the coastal areas weren't all dry. Evidence from rocks and sediments tells us that some coastal regions were hit by powerful seasonal monsoons, big storms that brought rain in short, intense bursts. Throughout the Triassic, Earth's overall climate was very warm. There were no ice caps at the poles, and ocean waters were relatively warm and sluggish, still recovering from the Great Dying. The lack of cold water currents meant lower oxygen levels in the oceans, making it harder for marine life to thrive. After the devastating extinction, the land looked barren and lifeless. In the early Triassic, the plant world was dominated by a few tough, fast-growing species like the strange spindly Pleuramia, a type of primitive fern. But as time went on, life began to rebuild. By the middle and late Triassic, the Earth was once again cloaked in forests, tall conifers, cycads, plants that looked like palm trees, and ginkgos spread across the landscape, creating homes and food for the growing animal populations. These forests laid the foundation for more complex food chains and healthier ecosystems. In the immediate aftermath of the Permian extinction, Earth's ecosystems were rough, simple, and dominated by a few lucky survivors. Paleontologists call these tough organisms disaster taxa, species that managed to hang on through the worst extinction in history. One of the most famous examples is Lystrosaurus, a strange creature about the size of a pig. It had a barrel-shaped body, stubby tusks, and a face something like a bulldog. Lystrosaurus was a type of dicynodont, a plant-eating member of a group known as synapsids, which are distant relatives of mammals. This resilient little animal managed to spread far and wide. Its fossils have been found in Antarctica, South Africa, India, and China, places that were all connected at the time as part of southern Pangea or Gondwana. It has even been nicknamed the Triassic Ark because it was one of the few animals that made it through the extinction and thrived afterward. Lystrosaurus likely survived because it wasn't picky about what it ate, could dig burrows, and may have been able to tolerate low oxygen levels, skills that gave it a huge advantage in the harsh world of the early Triassic Earth. As the planet recovered, new groups of animals began to appear and spread. Among the most important of these were the archosauromorphs, a group of reptiles that would give rise to both crocodiles and dinosaurs. Early archosauromorphs looked a bit like long-legged lizards. Many of them were small and agile, but they had major evolutionary advantages. Their lungs were more efficient, their bodies more upright, and their movements more powerful and energy efficient. These upgrades gave them a critical edge as ecosystems became more complex. By about 230 million years ago, the first real dinosaurs had arrived. At first, they weren't giants. These early dinosaurs were typically small, bipedal, walking on two legs, and built for speed. Some of the earliest known species include Eoraptor, Herrerasaurus, and Staurikosaurus, whose fossils were discovered in Argentina's Ischigualasto Formation, a rich fossil bed that preserves a snapshot of life from that time. These dinosaurs were agile hunters, no bigger than a modern human. Their sharp teeth suggest they ate meat, either by hunting small prey or scavenging. Their upright posture allowed them to move quickly, while their hands were likely used for grabbing or holding. Even so, these early dinosaurs weren't yet the dominant force on land. That title still belonged to other members of the archosaur family tree. While dinosaurs were still up-and-comers, a different group of archosaurs ruled the land, the Pseudosuchians, the ancient relatives of crocodiles. This group included a variety of powerful creatures. There were phytosaurs, which looked like crocodiles but had their nostrils high on their heads and lived in water. There were etosaurs, herbivores covered in heavy armor like tanks, and there were Rauisuchians, fierce predators that walked on land and looked like giant upright crocodiles. These animals were the top predators and herbivores of the Triassic world, while dinosaurs lurked in the background, waiting for their time to shine. While all this was happening, another group of creatures was quietly undergoing an evolutionary revolution. These were the cynodonts, the ancestors of mammals. Once dominant in the Permian period, most synapsids had been wiped out by the Great Dying, but a few survived. The cynodonts began to change in subtle but crucial ways. They evolved specialized teeth, sharp front teeth, pointed canines, and grinding molars. This allowed them to chew their food better, which is important for animals with high energy needs. They also developed a secondary palate, a bony roof that separated their breathing passage from their mouth, allowing them to chew and breathe at the same time. Their lower jaw started to change, with some bones shrinking and eventually becoming part of the middle ear, a key trait of true mammals. Fossils like Thrinaxodon and Cynognathes show this transition clearly. These creatures were still reptilian in many ways, but were starting to look and act more like mammals. Some scientists believe they were already warm-blooded, and even had whiskers and fur, giving them an edge in colder or more unpredictable climates. The Triassic period was a time of trial and error, of destruction followed by renewal. It saw the Earth recover from its worst extinction, and it witnessed the birth of new and powerful lineages that would shape the future. Dinosaurs began their long march to dominance. Mammal ancestors quietly refined the traits that would one day lead to us. The land baked under the sun of a giant supercontinent, while strange reptiles ruled the land and sea. It was a time of extraordinary transition, a laboratory of evolution in which the Earth's future rulers were forged. By the very end of the Triassic period, around 201 million years ago, something remarkable had taken shape, after millions of years of slow, steady change. This was the time when the very first true mammals finally appeared. These earliest mammals were tiny creatures, often no bigger than today's shrews. They likely spent most of their lives in the dark, active at night, using the cover of darkness to stay safe from the larger and more dangerous reptiles that roamed the land during the day. Their small size and nocturnal habits were not just quirks, they were key survival strategies. By being active at night and staying out of sight, these little mammals avoided competing directly with the massive, fearsome archosaurs that dominated the daylight hours. Instead of chasing the same prey, they carved out their own quiet corner of the food web. They hunted insects and other tiny invertebrates, things the larger reptiles ignored or couldn't catch. Though they lived alongside towering dinosaurs and terrifying predators, these tiny mammals were not just hiding in the shadows. They were following their own unique path through evolution. During this time, they were developing the special features that would one day define the entire mammal family. Warm-bloodedness, the ability to nurse their young with milk, sensitive hearing, and bigger brains in proportion to their body size. These traits didn't make them dominant yet, but they planted the seeds for a future when mammals would rise to greatness, long after the age of dinosaurs had come to an end. The Triassic period itself, lasting from about 252 million years ago to around 201 million years ago, was a time of constant change and fierce competition. The Earth was still recovering from the worst mass extinction in its history, and life was slowly filling in the empty spaces. For much of the Triassic, the land was ruled by a group of reptiles called pseudosuchians, distant relatives of modern crocodiles. They came in many forms and sizes, and for tens of millions of years, they were the top predators and plant-eaters of their time. The rivers and lakes were home to huge creatures called phytosaurs, which looked a lot like crocodiles, but were actually a different type of reptile. These beasts were the apex predators of the waterways. On land, herbivores called etosaurs lumbered around, covered in thick armour like living tanks. Then there were the Rauisuchians, fast, powerful hunters like the fearsome Postosuchus. These meat-eating reptiles were the terror of the land, and often much larger than the early dinosaurs they shared the world with. At this point in history, the dinosaurs were still small and not especially dominant. They weren't yet the rulers of the Earth, but rather survivors, quietly adapting and surviving in niches the larger reptiles didn't bother with. They may have been scavengers, small hunters, or opportunistic omnivores, slipping into roles that didn't attract too much attention from the bigger beasts. But the stage was already set for a dramatic shift. That shift came around 201 million years ago, at the very end of the Triassic, when the planet faced yet another mass extinction, the Triassic-Jurassic extinction event. Although not as devastating as the catastrophe that ended the Permian, this event still caused enormous upheaval. Scientists believe the cause was a series of enormous volcanic eruptions tied to the slow breakup of the supercontinent Pangea. These eruptions created what we now call the Central Atlantic Magmatic Province, a vast area of volcanic rock stretching across parts of today's North America, South America, and Africa. These massive eruptions released huge amounts of carbon dioxide and sulfur dioxide into the atmosphere. The result was rapid global warming, ocean acidification, and a cascade of environmental changes that pushed many living things to the brink. The dominant reptile groups of the late Triassic, especially the pseudosuchians, the etosaurs, the phytosaurs, and the Rauisuchians, were hit hard. Many of them disappeared entirely, but somehow the dinosaurs mostly survived. No one is completely sure why. It may have been because they could move more efficiently, or because they were able to eat a wide variety of foods, or simply because they were lucky. Whatever the reason, most of the main groups of dinosaurs made it through the extinction event. Once their main competitors were gone, the dinosaurs were free to grow larger, explore new roles in the ecosystem, and evolve into an amazing variety of shapes and sizes. In just a few million years after the extinction, during the early Jurassic period, the dinosaurs exploded in diversity. Giant sauropods, long-necked plant-eaters as long as buses, appeared, as did fierce theropods, the ancestors of later giants like Tyrannosaurus rex. This marked the true beginning of the age of dinosaurs. But it all started in the Triassic, which was not just a time of survival, but a critical turning point in the history of life. It was the testing ground where mammals, dinosaurs, and many other groups began their long evolutionary journeys. Our knowledge of the Triassic period has grown tremendously thanks to fossil discoveries all over the world. In Argentina, the fossil-rich Ischigualasto Formation has given us some of the best preserved early dinosaurs ever found, including Herrerasaurus and Eoraptor. In South Africa, scientists have uncovered fossils of ancient synapsids like the cynodonts, relatives of mammals, that help show the slow transition from reptile-like creatures to true mammals. In North America, the Chinle Formation has revealed a treasure trove of Triassic reptiles, offering a detailed look at the strange and diverse animals that lived alongside the earliest dinosaurs. Every fossil, whether a single tooth or a complete skeleton, adds a new piece to the puzzle of this fascinating era. Researchers are constantly re-examining old evidence, using new tools and technologies like CT scanning and computer modelling to learn more than ever before. The Triassic period stands as a shining example of life's incredible ability to recover, adapt, and innovate, even after the worst disasters in Earth's history. It was the dawn of new beginnings, a time when tiny mammals took their first steps, and dinosaurs began the long rise to dominance that would shape the next 135 million years of life on Earth. Imagine a world so huge and connected by land that you could, at least in theory, walk all the way from the South Pole to the North Pole without ever needing to cross a single ocean. That was the incredible reality of Pangaea, a gigantic supercontinent that shaped the face of the Earth for an astonishing length of time, from the late Paleozoic era through the early Mesozoic era, spanning hundreds of millions of years. This was not just a collection of continents squished together. It was almost all of Earth's landmass united into one massive block. Its immense size didn't just change the way the planet looked, it also changed how the entire Earth worked, especially the climate. In today's world, we're used to a globe made up of scattered continents and oceans, each with its own weather systems and climates. But back when Pangaea ruled the Earth, everything was on a much grander scale. This single supercontinent created its own massive and extreme climate system, one that was nothing like what we experience today. While the outer edges, near the oceans, enjoyed milder, wetter conditions, the inner regions were scorching, dry, and unforgiving. Understanding Pangaea's climate isn't just about ancient weather. It shows us how much the layout of land and sea can influence winds, rainfall, ocean currents, and even life itself. The most dramatic part of Pangaea's climate was found right in the middle of the continent. Imagine a land so wide and so deep that even the moist ocean winds, after travelling thousands of miles, would run out of steam, or rather water, long before reaching the centre. By the time these winds arrived, they were dry and useless for bringing rain. This left the heart of Pangaea in a permanent state of drought, and not just an ordinary desert. This was a super desert, stretching across areas that today are parts of North America, South America, and Africa. These lands were covered in enormous sand seas, called ergs, with massive sand dunes endlessly shifting in the wind. Between the dunes lay dry salt flats and seasonal lakes that would briefly fill with water during rare rains, only to evaporate quickly under the blazing sun, leaving behind thick crusts of salt and minerals. The air would have been dusty and often coloured red from tiny iron-rich particles in the soil, minerals that had rusted in the dry air. We know this because scientists have found thick layers of reddish rock, called red beds, across many of today's continents. These rocks, along with deposits of minerals like gypsum and rock salt, tell a clear story of ancient dryness and intense heat. Even the plants and animals that lived there had to be tough. Early conifers and cycads grew with waxy leaves to hold on to moisture, and deep roots to reach hidden water. The creatures that lived there had to be just as hardy, built for survival in an environment where water was always scarce. The sheer width of Pangaea meant that this dry zone was enormous, too far from the ocean for moist air to reach it, creating a climate system that was isolated and harsh. Now, if you had made your way from that scorching desert toward the coast, you would have seen a completely different world. Thanks to the surrounding Panthalassic Ocean and the large Tethys Ocean tucked into one side of the continent, the coastal regions had much more pleasant weather. These areas, which would later become parts of Europe, Asia, Australia and the edges of Gondwana, enjoyed more humidity, regular rainfall and gentler changes in temperature. Because they were so close to the ocean, the air was full of moisture, which rained down often, creating lush landscapes filled with forests, rivers and swamps. And we have plenty of proof. Massive coal deposits, laid down during the Carboniferous and Permian periods, from about 359 million to 252 million years ago, come from this time when Pangaea was forming and at its largest. These ancient coal beds are the remains of huge tropical forests that once thrived in the warm, wet lowlands of Pangaea's edges. Giant plants like lycopods, ferns and horsetails covered the land, soaking in the rain and growing into dense jungles that would later turn into the coal we burn today. And just offshore, the oceans teemed with life. Fossils of marine creatures, coral reefs and shell beds line the ancient coastlines, showing that these were healthy, vibrant environments. The ocean currents, although scientists are still piecing together their exact paths, would have helped carry heat and moisture around the supercontinent, making life along the coast more comfortable and diverse compared to the dry, dusty heartland. So, in the age of Pangaea, Earth was a land of extremes. Its massive size and unique shape created a world where deadly dry deserts stretched across its core, while lush, green coasts hugged the edges, all shaped by the great forces of land, sea, and air. It's a powerful reminder that the arrangement of continents is not just a mapmaker's concern. It's one of the most important drivers of life and climate on Earth. One of the most remarkable and awe-inspiring effects of Pangaea's enormous size was the creation of a gigantic seasonal weather pattern known as the supercontinental monsoon. Today, monsoons are seasonal wind patterns that happen because land and ocean heat up and cool down at different speeds. But back in the time of Pangaea, this natural effect was intensified to an almost unimaginable level because the landmass was so incredibly vast. During the summer months, Pangaea's massive interior would heat up much faster than the surrounding ocean, called the Panthalassic Ocean. The land would become scorching hot, while the ocean stayed relatively cooler. This created a powerful difference in air pressure. A low-pressure zone formed over the supercontinent's hot interior, while a higher pressure zone lingered over the cooler ocean. This strong pressure difference pulled in huge volumes of moist oceanic air toward the continent. As a result, Pangaea experienced monsoon rains on a massive scale, far greater than anything we see in today's world. Moisture-laden winds brought relentless summer downpours to many parts of the supercontinent, especially near the coasts. Rivers swelled with water, entire regions flooded, and even areas farther inland received enough rain to turn dry plains into thriving green landscapes, at least for a time. But when winter arrived, the pattern reversed. The land cooled down much more quickly than the ocean, causing the air above Pangaea to become dense and heavy. This created a strong high-pressure system over the continent, while the ocean remained warmer and at lower pressure. Now, dry and chilly winds blew outward from the land toward the sea, creating a harsh dry season that swept across most of Pangaea. These dramatic seasonal shifts, from flooding rains to bone-dry winds, shaped the land in profound ways. The repeated cycle of wet and dry seasons left behind clear signs in the geological record. Rivers carried sediments during the rainy season, depositing alternating layers of coarse and fine particles known as rhythmites, a kind of natural layering that marks the passing of the seasons. Ancient soils, called paleosols, also reveal signs of these seasonal changes, showing clear patterns of wet and dry weather. Fossilized plants found in these regions tell us even more. Many species developed ways to survive the dry months and flourish when the rains returned, showing how life adapted to this extreme climate. Because Pangaea was so immense, this super monsoon system didn't just affect a single region. It influenced weather patterns across much of the planet, It became a kind of global climate engine, far stronger and more widespread than the monsoon systems we experience today. But that wasn't the only extraordinary climate event tied to Pangaea. Around the same time as the supercontinent's formation, the Earth went through a major ice age known as the Permo-Carboniferous glaciation. This was not just a brief cold spell in one area. It was a planet-wide event that covered huge portions of land with thick sheets of ice. This ice age began more than 300 million years ago, when a large part of the southern supercontinent Gondwana, which included present-day Africa, South America, Antarctica, Australia and India, slowly drifted over the South Pole. As these land masses sat over the coldest region on Earth, snow kept falling but didn't melt during the summer months. Over time, the snow built up into massive glaciers and ice sheets. Another major reason for this ancient ice age was a drop in atmospheric carbon dioxide. During the Carboniferous period, huge forests grew and formed massive coal beds. As trees and plants died, their remains were buried and trapped underground, locking away large amounts of carbon and lowering the levels of CO2 in the atmosphere. With less of this greenhouse gas, Earth's temperature dropped, helping glaciers spread even farther. There were other contributing factors too. As continents moved and joined together, they changed the way ocean currents flowed. Some seaways were closed off or restricted, which shifted the planet's heat distribution and allowed more ice to form near the poles. The evidence for this ancient glaciation is found all across the southern continents. Geologists have discovered tillites, which are special rocks formed from the debris left behind by glaciers. In many places, they also found striated pavements, rock surfaces scratched and grooved by the slow, grinding movement of giant ice sheets. U-shaped valleys carved by glaciers and drop stones, large rocks dropped into fine sediments by melting icebergs, add even more proof. As millions of years passed and Pangaea slowly began drifting northward, the ice sheets began to melt, and Earth entered a warmer phase during the Triassic and Jurassic periods. This shows how complex and ever-changing Earth's climate can be, driven by the movement of continents, changes in atmospheric gases, and even the planet's orbit around the Sun. Pangaea didn't just affect land and ice, it also changed the behaviour of the oceans and the atmosphere on a global scale. Surrounding this massive landmass was the Pangaea Ocean, a vast, uninterrupted body of water that covered most of the planet. Unlike today's oceans, which are divided into separate basins by continents, Pangaea allowed enormous ocean currents to move freely across the globe. This may have made deep-sea circulation patterns simpler and possibly more stable in some regions. Near Pangaea's eastern side lay the Tethys Ocean, a warm, shallow sea that acted like a giant heat battery. It played a key role in regulating temperatures and mixing water with the larger Pangaea Ocean. The interaction between these two water bodies would have created unique and powerful ocean currents that don't exist today. In the air, things were just as unusual. The basic structure of Earth's atmosphere, the rising and falling air cells we now call Hadley, Ferrel, and polar cells, still existed. But Pangaea's gigantic landmass made everything more intense. With such a large area heating and cooling so dramatically, the seasonal high and low pressure systems were more extreme, powering the vast super monsoons. Because Pangaea lacked many mountain ranges, most of which formed later, there were fewer obstacles to block the wind. This meant air could move more easily and cover greater distances. Climate changes in one region of the supercontinent could affect areas thousands of miles away, through a kind of global weather connection known as a teleconnection. For example, a shift in monsoon strength in one place could change rainfall patterns in far-off areas. The Pangaea Ocean, with its vast supply of moisture, made the contrast between the wet coastal regions and the dry inland areas even more dramatic. The coasts were lush and green, while the interior was dry and often harsh, especially during winter. However, Pangaea's unique climate, with its scorching summers, frigid winters, violent monsoons and icy interludes, shaped life in extraordinary ways. Plants and animals in the dry interior evolved to survive with little water, while the rainy coast supported thriving ecosystems full of diverse species. Since there were no oceans between the continents, animals and plants could spread far and wide, leading to less regional variety compared to today's world. The tale of Pangaea is not only about how it majestically came together to form one giant supercontinent, it's also about how, in time, it was torn apart. Just like the great supercontinents that came before it, Pangaea was never meant to last forever. It was always fated to break apart, slowly but surely, under the powerful invisible forces deep within the Earth, forces we now call plate tectonics, which constantly shift and reshape the surface of our planet. But Pangaea didn't shatter in a single sudden disaster. Its breakup was a slow, drawn-out drama that played out over tens of millions of years. This long separation began toward the end of the Triassic period, around 200 million years ago, and continued well into the Jurassic period. The first signs that something was changing were quiet, almost unnoticeable. The Earth's crust began to feel pressure building deep beneath it. Then came gentle swelling of the land, like a great breath being held. Eventually the crust began to crack, forming enormous rift valleys, long deep scars stretching across the supercontinent's surface. Understanding how and why Pangaea broke apart is key to understanding why our continents and oceans look the way they do today. The ancient fractures left behind can still be found in rocks and landforms across the globe, acting like pages from Earth's diary. These geological clues help scientists piece together the dramatic story of how the continents we live on were once part of something far larger, and how they were torn away from one another. But why do these mighty supercontinents, after forming so grandly, eventually fall apart? That question takes us to the very heart of Earth's inner workings. Inside the Earth, far beneath the surface, the mantle is constantly moving. Slow, swirling currents of hot rock flow in great circles, much like water boiling in a pot. These currents are part of the reason continents move. One powerful idea explaining why continents start to rip apart is called the supercontinent insulator effect. Imagine Pangaea as a massive thick blanket laid over the planet's surface. Because it covered so much of the Earth, it acted like insulation, trapping the heat rising from the deep interior. This heat was mostly created by the slow breakdown of radioactive elements buried far below. Over millions of years, the heat built up under Pangaea's crust, making the mantle beneath it hotter and lighter. As this superheated mantle rose upward, it pushed against the crust above, causing the land to bulge and stretch. Just like a piece of toffee that stretches and finally snaps, the crust began to tear. Cracks and faults began to appear, marks of a supercontinent starting to split. And that's not all. Another important player in this story is the mantle plume. A mantle plume is like a hot pillar of rock that rises from the deepest parts of the Earth, possibly from the boundary between the Earth's core and mantle. When a plume reaches the underside of the crust, it creates a hot spot where volcanic activity can erupt to the surface. These plumes bring not only heat, but also pressure, pushing the crust upward even more and making it easier to break. One of the most dramatic examples of such activity is something called the Central Atlantic Magmatic Province, or CAMP for short. This massive volcanic event happened around 200 million years ago, right as the Atlantic Ocean was beginning to form. CAMP was one of the largest lava flooding events in Earth's history, pouring out millions of cubic kilometers of molten rock over what are now parts of North America, South America, Africa, and Europe. The size of this event suggests it was caused by one or more huge mantle plumes, and it likely played a major role in weakening Pangaea's crust and helping the continents begin to drift apart. In today's world, the movement of plates is mostly driven by forces like slab pull, where heavy oceanic plates sink into the mantle, and ridge push, where new crust forms and spreads at mid-ocean ridges. But back then, during the early stages of Pangaea's breakup, the biggest force was coming from inside. Heat rising from the mantle was pushing the land masses apart from within. The early signs of this rifting weren't oceans forming overnight. Instead, it started with slow, broad swelling of the land as hot material rose from below. This uplift created high, wide plateaus. As the crust stretched and thinned, cracks began to form. These cracks evolved into networks of faults, where blocks of crust shifted up and down. The down-dropped blocks became grabens, long, low valleys, while the raised blocks became horsts, higher ridges alongside the valleys. These grabens were the earliest rift valleys, the first visible signs that Pangaea was beginning to break. As the crust split and thinned, pressure on the mantle dropped, allowing it to melt and produce magma. This molten rock surged upward through the cracks, leading to enormous volcanic eruptions. These eruptions spread out huge layers of lava, called flood basalts, covering large areas with dark rocky plains. Again, Camp is a perfect example of this, with its vast stretches of ancient lava still visible today. These eruptions show how much heat was moving from the Earth's interior to the surface, a sure sign of a major geological event unfolding. The places where Pangaea started to split eventually became the birthplaces of the modern oceans. One of the most important of these was the Central Atlantic Rift System, where the Atlantic Ocean first began to open. This rift formed between what are now North America and Africa, and later extended south to divide South America from Africa, creating the South Atlantic Rift System. But this didn't happen all at once. At first, the rift appeared as a series of broken basins, long, narrow valleys that stretched for hundreds of miles. Over millions of years, these basins gradually connected and widened. Some of these ancient rift basins can still be seen today. One example is the Newark supergroup along the eastern United States, where layers of river and lake sediments, mixed with lava and volcanic ash, tell the story of the land tearing itself apart. A similar process happened farther south, eventually pulling South America and Africa apart piece by piece. To see a modern version of this ancient process, scientists often look at the East African Rift System. This is a place where Africa is literally being torn in two. In East Africa, you can see wide stretches of uplifted land, deep faults forming grabens and horsts, chains of active volcanoes, and long lakes that have filled in the valleys. It's a living laboratory showing the same forces that once broke Pangaea are still active today. But it's worth noting that not all rifts succeed in becoming oceans. Some try to split but never make it all the way. These are called failed rifts, or aulocogens. They are like forgotten scars in the crust, places where the land once began to tear but never fully separated. Over time, these areas often collect thick piles of sediments and can sometimes reactivate under new tectonic stresses. Some of these failed rifts still play important roles today. For example, the Bennu Trough in West Africa was a failed branch of the South Atlantic Rift. In the United States, the Reelfoot Rift in the central part of the country is a remnant of a failed rift linked to the ancient Iapetus Ocean, which existed long before Pangaea. These failed rifts are like time capsules, preserving layers of Earth's past and often holding valuable resources like oil and gas. The story of how Pangaea broke apart is written all across the surface of our planet, not in one place, but in many different ways, studied by scientists from many different fields of geology. One of the clearest clues comes from the rocks left behind in deep cracks and valleys that formed as the giant supercontinent began to split. These valleys, called rift valleys, started to open up as the Earth's crust was pulled apart. As they sank lower, they created big basins that filled up with mud, sand, gravel, and even entire river and lake systems. These rift valleys collected layers of sediment over time. Rivers and lakes left behind rocks like sandstone, shale, and conglomerate, all made from ancient sediments that settled in water. One common feature in these deposits is what geologists call red beds. These are reddish-coloured rocks, stained by iron minerals that rusted in the open air. Their colour tells us something important. The climate at the time was often hot and dry, just like deserts today. In places where the rift valleys were partly closed off, and ocean water sometimes flowed in and then dried up, thick evaporate deposits formed. These include layers of halite, better known as rock salt, and gypsum, a soft mineral used in plaster. These minerals formed from repeated cycles of flooding and drying, like a salty pond that keeps evaporating in the sun. These salt layers aren't just geological oddities, they're also important for finding oil and natural gas, because they can trap these valuable resources beneath them. In wetter parts of the rift system, or during rainier times in Earth's history, swamps and lush plant life grew. These swampy areas could later turn into coal seams, showing us that not all rift valleys were dry and dusty. Some were green and full of life. But perhaps the most dramatic evidence of Pangaea's breakup comes from igneous rocks, those formed from magma that erupted from deep underground. As the Earth's crust stretched and thinned, molten rock from the mantle poured out in massive lava floods. These became huge fields of basalt, dark volcanic rock, covering vast regions. Some of the most famous of these include the Central Atlantic Magmatic Province, the Paranaia-Tendeka Province shared by South America and Africa, and the Karoo Province in southern Africa. These lava flows were so enormous that they sometimes cooled into hexagonal columns, a striking feature known as columnar jointing. But it wasn't just lava on the surface. Underground, magma squeezed into cracks and spread horizontally and vertically, creating structures called dikes, vertical sheets, and sills, horizontal sheets. These are like the plumbing system of a rift zone, frozen pipelines of molten rock. When scientists study the chemical composition of these volcanic rocks, they can figure out where the magma came from, often directly from the Earth's mantle, pulled upward by the stretching of the crust. On a structural level, one of the clearest signs of rifting is the presence of normal faults, breaks in the Earth's crust where one side moves downward as the crust is pulled apart. These faults can be seen on maps of surface geology, or more impressively through seismic imaging, which uses sound waves to see deep into the Earth. These surveys reveal classic graben and horse structures, sunken blocks and raised blocks that form when the crust stretches. In many places, these old rift valleys are now buried under thousands of meters of younger sediments, but special geophysical tools like gravity mapping and seismic reflections still allow scientists to detect the thinned crust beneath. Another fascinating line of evidence comes from paleomagnetism, the study of the Earth's ancient magnetic field. As volcanic rocks cool, tiny magnetic minerals inside them line up with the direction of the Earth's magnetic field at that time. By studying these patterns in rift zones, geologists can tell when the rifting happened and how fast the continents moved apart. Once rifting gives way to seafloor spreading, the ocean floor captures this magnetic record in symmetrical stripes on either side of the mid-ocean ridge. These magnetic stripes act like a barcode, helping scientists precisely date when the ocean began to open and when the continents began to drift away from each other. Even fossils help tell the story of Pangea's breakup. While they don't show rifting directly, they provide strong indirect evidence. For example, the fossil remains of a small pig-sized reptile called Lystrosaurus have been found in Africa, Antarctica, and India, all separated by oceans today. This suggests that these continents were once joined together, part of the vast landmass of Pangaea. After the continents split, each species went its own way, evolving differently, which provides a kind of biological timeline that matches the geological one. Eventually, the rifting process reaches its final stage, when the continental crust splits completely and magma rises from the mantle, not just through cracks, but to form new oceanic crust. This is how a new ocean begins to form. A great example of this happening today is the Red Sea, the long narrow stretch of water between Africa and the Arabian Peninsula. It is a modern-day rift zone, where the crust is being pulled apart and new seafloor is starting to form, just like what happened when Pangaea first began to break. To sum it all up, the breakup of Pangaea was one of the most powerful and slow-moving transformations our planet has ever seen. It didn't happen suddenly, but over millions and millions of years. It began with the crust stretching and cracking, with rivers and lakes forming in sunken valleys, with volcanic eruptions spilling vast lava flows, and with thick deposits of salt and coal slowly building up. It was a time of tension, fire, and change. Today, the evidence is everywhere. In the twisted rocks, the faults, the volcanic scars, and the matching fossils found oceans apart. These geological scars are the fingerprints of Pangaea's slow and dramatic breakup. They remind us that our planet's surface is never still. Continents continue to drift, break, and sometimes come back together in a never-ending cycle. The Earth, always in motion, carries the memory of Pangaea deep in its bones. Imagine the Earth not as a still and silent rock, but as a living, breathing giant, one with a fiery heart and a restless spirit. Beneath our feet, deep inside this planet, powerful forces are always moving, reshaping the surface above us. For hundreds of millions of years, the continents have been drifting around like slow-moving puzzle pieces. Sometimes they crash into each other, forming giant supercontinents like Pangaea, and other times they break apart in spectacular fashion, creating new oceans and changing the face of the planet forever. But what incredible force could cause something so vast and solid to move, split and change so dramatically? What hidden engine lies beneath the ground, quietly controlling the fates of entire continents? Many scientists believe the answer lies deep inside the Earth, in massive fiery phenomena known as mantle plumes and hotspots. These are not just random geological features, they are like the Earth's internal furnaces. They send up tremendous amounts of heat from the deep interior, giving us important clues about how the ground beneath us moves over millions of years. To really understand these mysterious forces, let's take a journey into the depths of the Earth, far below the surface where mountains rise and rivers run. Down there, things are not as calm and steady as they seem above. The Earth's interior is a swirling, bubbling world of heat and slow motion. Between the Earth's solid crust and its super-hot molten outer core lies a massive layer called the mantle. It stretches for thousands of kilometers and behaves, over long periods of time, more like a thick, sticky liquid than a solid rock. It flows very slowly in a process called convection. Think of a giant pot of stew simmering on the stove. As the bottom heats up, the hotter stew rises to the top, while the cooler stew at the surface sinks back down. This constant churning motion is similar to what happens in the mantle, except the process takes millions of years instead of minutes. Now, mantle plumes are like enormous columns of unusually hot rock that rise straight up through this slow-moving stew. Many geologists believe that these plumes begin their journey from a mysterious boundary deep inside the planet, right at the place where the mantle touches the Earth's outer core. This hidden zone, nearly 3,000 kilometers below our feet, is known as the D-double prime layer. The temperatures down here are unbelievably high, almost as hot as the surface of the sun. In this scorching region, some parts of the mantle get so hot that they start to rise upward. Imagine a hot air balloon lifting off the ground. The heated air inside is lighter than the cooler air outside, so it floats up. The same thing happens with mantle plumes. The superheated rock becomes slightly less dense than the surrounding mantle, and it begins a long, slow rise toward the surface. This rise isn't chaotic, it's surprisingly organized. A typical plume forms a shape that looks like a mushroom, a long, narrow tail that stretches all the way from the deep earth, and a large, round head at the top. This wide plume head, often measuring hundreds or even over 1,000 kilometers across, spreads out just beneath the Earth's surface. When it reaches the bottom of the Earth's rigid outer layer, called the lithosphere, which includes the crust and upper mantle, it starts to cause major changes. First, the sheer heat and pressure from the plume push the lithosphere upward, like someone pressing their hand up from beneath a soft carpet. This causes a bulge or dome on the surface that can rise hundreds of meters, or even more than a kilometer, into the air. This upward push stretches the crust, making it thinner and more fragile, much like a rubber band that's being pulled too far. Eventually, this stretched crust starts to crack, forming deep, narrow valleys known as rift valleys, where the ground begins to tear apart. But that's just the beginning. The intense heat from the plume also melts part of the mantle rock directly beneath the crust. This produces massive amounts of magma, or molten rock. Because magma is lighter than solid rock, it rises up through the cracks and faults in the lithosphere, leading to huge volcanic eruptions on the surface. These are not your average volcanoes. They are truly colossal eruptions, the kind that can cover entire regions with lava. Scientists call these events large igneous provinces. Some of these ancient lava flows were so massive that they covered areas as big as entire countries. In fact, famous examples like the Deccan Traps in modern-day India and the Siberian Traps in Russia are thought to be the result of past mantle plume activity. These formations are made of thick layers of solidified lava, and they are silent witnesses to the incredible power of the Earth's deep interior. This whole process, where heat from deep inside the planet causes the surface to bulge, crack, erupt, and eventually split apart, is not just a poetic idea. It's a real and fundamental part of how continents break up. The rising plume weakens the crust from below. The uplift creates slopes that gravity pulls on. The crust thins out and becomes more likely to break. The lava that erupts further softens and lifts the ground, and eventually the entire region may split wide open. In some cases, this even marks the beginning of a new ocean, as the two halves of a continent begin drifting away from each other, a new oceanic crust forms between them. A classic example of this process may have played out during the breakup of the ancient supercontinent Pangaea. Imagine Pangaea as one gigantic landmass, holding nearly all of Earth's continents together. Around 200 million years ago, powerful mantle plumes are thought to have risen beneath its interior. These plumes would have caused broad uplift and enormous volcanic eruptions. The enormous outpouring of lava would have formed a vast volcanic plateau. All this internal heat and activity would have weakened the thick crust of Pangaea, making it vulnerable to the pulling and pushing of tectonic forces. Eventually, the combination of internal heat and external stress may have been too much. Cracks formed, continents pulled apart, and the once unified Pangaea began to break into the smaller continents we know today. So in a very real sense, the fire deep beneath the Earth helped tear a supercontinent in two, and continues to shape our planet to this very day. Hotspots are the surface signs of something much deeper and more dramatic happening far below our feet. When a plume of superheated material rises from deep inside the Earth and begins to melt the rigid layer above it, called the lithosphere, it creates a steady, long-lasting source of volcanic activity. The most fascinating thing about many hotspots, such as the famous one beneath the Hawaiian Islands, is that they stay more or less in the same place within the Earth's mantle, but the Earth's surface, made of tectonic plates, is constantly moving. So, as a plate drifts slowly over this fixed hotspot, the intense heat keeps punching through the moving plate, creating a chain of volcanoes one after another. The result? A trail of volcanic islands, with the newest and most active volcano sitting right above the hotspot, and the older ones trailing behind like footprints. Picture a conveyor belt slowly gliding over a glowing heat lamp. The lamp doesn't move, but as the belt rolls over it, a line of burnt marks appears. That's exactly what happens with these volcanic chains. These hotspot tracks give scientists valuable clues, not just about how volcanoes form, but also about how Earth's tectonic plates have moved across the globe over millions of years. They are strong evidence that mantle plumes come from deep inside the planet, far below the shallower zones where most volcanic activity takes place. But how exactly does volcanic activity help us understand changes in Earth's tectonic plates? The answer lies in how big, how explosive, and where the eruptions happen. Sometimes we find massive volcanic eruptions that cover huge areas with lava in just a few million years, which in geological time is extremely fast, almost like a blink. These are called flood basalt events, and they are a type of volcanism connected to what scientists call large igneous provinces, or lips. These eruptions are far more intense than the slow lava flows at mid-ocean ridges, or the explosive cone volcanoes at subduction zones. Flood basalts tell us that something extraordinary is happening below the surface, an immense surge of heat and magma rising straight from the mantle, and there's more. The chemical makeup of the lava from these eruptions tells us where it came from. Many of these lavas are a special kind known as tholeiitic basalts. These form when rock deep in the Earth's mantle melts, rather than when shallow crust melts. This geochemical fingerprint helps scientists distinguish deep mantle plumes from other volcanic activity caused by things like the stretching of the continental crust, which often produces lava rich in silica. But one of the most important clues is where these huge eruptions happen. If they occur far away from the edges of tectonic plates, in the middle of a continent, then it's a big hint that a mantle plume is at work. Most volcanic activity takes place at plate boundaries, where plates are either crashing into each other, pulling apart, or sliding side by side. So, when volcanism happens right in the center of a tectonic plate, it often means that a massive hot plume from deep inside the Earth has reached the surface, pushed up the crust, and caused it to crack open. This is exactly what happened during the early stages of the breakup of Pangaea, the giant supercontinent that once held most of Earth's land together. Around 200 million years ago, enormous volumes of lava burst forth across areas that would later become parts of North America, South America, Africa, and Europe. These floods of lava were the Earth's dramatic warning that Pangaea was beginning to tear apart under the pressure from within. The process usually unfolds in a predictable order. First, the rising head of the mantle plume pushes up on the lithosphere, causing the crust to bulge and stretch. This stretching forms rift valleys, like deep cracks or trenches. Then, As the crust thins and heat builds up, vast amounts of magma are released and spread out across the surface in enormous lava flows, the flood basalts. This intense volcanic activity marks a point of no return. The crust is now weakened so much that it starts to split, setting the stage for new ocean basins to form. In many cases, this volcanic phase happens shortly before seafloor spreading begins. You could think of it as the Earth's fiery overture, a dramatic opening act before the full breakup of a continent. A perfect example is the Central Atlantic Magmatic Province, or CAMP. This gigantic outpouring of lava happened around 200 million years ago, right at the seams where Pangaea was getting ready to split apart. The location and timing of CAMP are no coincidence. They show a direct link between this massive volcanism and the forces that opened up the Atlantic Ocean. It was as if the Earth was sounding a loud alarm, announcing the tectonic upheaval that would completely reshape its surface for millions of years to come. And even after a continent breaks apart, mantle plumes and hotspots don't stop their work. As tectonic plates keep drifting over these plumes, they leave behind those beautiful chains of volcanic islands we see in places like Hawaii. But these island chains aren't just eye-catching scenery. They are like a geological map showing the path and speed of plate movement over immense stretches of time. Each island or seamount is a marker, a piece of a puzzle that tells the story of Earth's moving plates. However, the tale of mantle plumes and hotspots is one of incredible power, rising from the Earth's depths to shape its surface. These deep fiery plumes deliver vast amounts of heat and molten rock to the outer shell of our planet. That energy can lift the land, stretch it apart, and eventually crack it wide open. The massive volcanic outbursts they cause, especially the formation of large igneous provinces, are unmistakable signs that the Earth is undergoing a major transformation. They are not random or routine. They are the Earth's way of speaking to us, warning that a supercontinent like Pangaea is under pressure and is about to be torn apart, giving birth to new oceans and a whole new chapter in our planet's ever-changing story. Imagine a long time ago, hundreds of millions of years in the past, when nearly all the land on Earth was joined together as one enormous supercontinent. This was Pangaea, a truly gigantic landmass that stretched from the icy South Pole all the way to the frozen North Pole. It was a world of ancient deserts that blistered under scorching suns and of mighty mountain ranges, now long worn down by time, that rose high into the skies, silent monuments to the epic collisions of continents that had created this vast superland. For a huge part of Earth's deep history, life, both on land and in the oceans, existed in a world where the idea of continents slowly drifting apart was, for the moment, paused. The planet's crust seemed steady, its continents locked together in a strange ancient unity. But deep below the surface, massive forces were quietly building. Even the grandest structures are never permanent, and Pangaea, no matter how vast, was destined to crack and fall apart. Its slow and dramatic breakup was one of the most extraordinary geological events our planet has ever witnessed. This wasn't something that happened overnight. It was a long, messy and fiery process, and the first major chapter of this earth-shattering story was the birth of the Atlantic Ocean, a moment in time that began with one of the largest volcanic events the world has ever seen, the creation of the Central Atlantic Magmatic Province, or CAMP. But before we dive into this fiery beginning, let's understand how Pangaea came to be. Pangaea was not formed all at once. It came together gradually, over tens of millions of years, as ancient continents collided and merged. By around 300 million years ago, these collisions had united nearly all of Earth's land into a single, massive supercontinent. Pangaea's formation deeply affected Earth's climate, the movement of its ocean currents, and the course of evolution itself. But beneath its heavy and widespread surface, powerful forces were at work. Deep inside the Earth, heat was constantly rising from the mantle, setting up slow-moving currents like thick soup in a boiling pot. These currents built up stress beneath Pangaea's crust, so much so that the land above began to feel the pressure. At first, the signs of this coming change were subtle. Pangaea didn't explode or collapse suddenly. Instead, it began to stretch slowly, so slowly in fact, that it would have been impossible to notice in a human lifetime. This early phase, called continental rifting, was a bit like pulling on a thick piece of dough. At first it just stretches, then it thins in the middle, and eventually it tears. As Pangaea stretched, the continental crust began to split apart. This tearing created a patchwork of long cracks and sunken valleys known as rift valleys, grabens, which are blocks of land that sink down between faults and half-grabens. These became long, narrow basins that would later evolve into the very early beginnings of the Atlantic Ocean. Rivers flowed into these deepening cracks, carrying mud, sand, and other sediments. Over time, these materials piled up layer upon layer, leaving behind a detailed geological record of this dramatic period in Earth's history. But then came a moment of true geologic spectacle, a massive, fiery event that turned the slow rifting of Pangaea into a full-blown breakup. This was the eruption of the Central Atlantic Magmatic Province, or CAMP, and this was no ordinary volcanic episode. It was one of the most gigantic outpourings of lava the Earth has ever seen. This cataclysmic event happened around 200 million years ago, right at the dividing line between the Triassic period and the Jurassic period. CAMP is one of the largest igneous provinces on the planet, meaning it involved the creation of vast areas of solidified volcanic rock, and the timing of this eruption wasn't random. It lined up almost perfectly with the moment when Pangaea first began to split and the Atlantic Ocean started to form. The scale of this eruption is nearly beyond imagination. Lava from CAMP spread across what are now North America, South America, Northwestern Africa, and Southwestern Europe, 4 continents that, at the time, were all still connected as part of Pangaea. The total amount of magma that erupted during CAMP's activity is estimated to be between 2 million and 4 million cubic kilometers. That's enough lava to bury entire countries under several hundred meters of solid rock. To compare, think of the eruption of Mount Tambora in the year 1815, the largest volcanic eruption in all of recorded human history. Now multiply that by thousands, perhaps tens of thousands. That is the kind of raw power we're talking about. These eruptions didn't come from tall, conical volcanoes like the ones in movies. Instead, they were effusive eruptions. Lava poured out in great sheets, flooding entire landscapes and forming massive layers of dark basaltic rock known as flood basalts. When scientists look at the lava from CAMP today, they find a very specific type of volcanic rock called tholeiitic basalt. This rock forms when material melts deep within the Earth's mantle and rises to the surface. This kind of lava tells us that the CAMP eruptions were not just surface-level events. They came from deep inside the Earth, possibly triggered by the rise of a massive mantle plume. A mantle plume is a huge column of hot rock that rises from deep inside the Earth and melts everything in its path. When this plume hit the underside of Pangaea's crust, it would have caused enormous melting, lifting, and eventually massive eruptions. Most of the lava from CAMP erupted over a short span of time, geologically speaking, perhaps as little as 1 million to 5 million years. This concentrated activity, happening right as the Atlantic Ocean was just beginning to open, suggests that CAMP didn't just coincide with Pangaea's breakup, it helped cause it. The intense heat and pressure from the plume weakened the crust, which was already stretched thin. It was like applying heat to a sheet of glass that's already cracking. It finally shattered. The Earth split open, and from that split a brand new ocean, what we now call the Atlantic Ocean, was born. In a way, it was as if the Earth itself had reached a breaking point. The deep, fiery forces from its core surged upward in a spectacular release, ripping open the crust and marking the end of Pangaea's reign. From then on, the single world continent would be no more. It would give way to the world we know today, a world of drifting continents, vast oceans, and a planet forever shaped by the forces that once shattered the greatest landmass in Earth's history. To truly understand how the Atlantic Ocean came to be, we need to first imagine something called a proto-ocean. This isn't a wide, deep ocean like the Atlantic we see on maps today. A proto-ocean is more like a baby ocean, just starting to form. It's long and narrow, like a giant crack splitting the Earth's crust open. This early ocean has brand new oceanic crust forming at its centre, fresh rock created from melted material rising up from deep inside the Earth. That rising molten rock cools and hardens to create the ocean floor in a process known as seafloor spreading. When continents begin to pull apart, the thick crust beneath them eventually rips open. As it does, the hot mantle from below starts to rise, melts due to the decrease in pressure, and forms new crust right along the centre of this opening. This is how new oceans begin, slowly, painfully, and with a great deal of fire and heat. The early Atlantic, or proto-Atlantic, probably looked a lot like the modern Red Sea today. A long, narrow stretch of water with hot crust beneath it, and fiery volcanic activity bubbling along its centre. The Atlantic Ocean didn't just appear all at once, it grew gradually. The opening began somewhere near the middle, and then spread northward and southward over time. One of the earliest signs of this grand event came with the camp eruptions, that is, the Central Atlantic Magmatic Province, a vast region of volcanic activity that marks the first major rupture between what would later become North America on one side, and Africa and South America on the other. As this rift kept growing wider, the seafloor spreading continued. Along the growing crack known today as the Mid-Atlantic Ridge, new ocean crust kept forming. This ridge is like a massive underwater mountain chain that runs down the spine of the Atlantic Ocean. Even now, it's still active, still creating new seafloor, still pushing the continents apart. We know all of this happened thanks to many pieces of evidence gathered by geologists. One of the clearest clues comes from magnetic stripes in the oceanic crust. As new rock forms at the spreading centre, it records the direction of Earth's magnetic field at that moment. But Earth's magnetic field has flipped many times over millions of years, so the ocean floor ends up with alternating stripes of normal and reversed magnetism. These stripes are like a barcode, perfectly mirrored on each side of the Mid-Atlantic Ridge. They tell us exactly how, when, and where the seafloor formed and help us map out the history of the ocean's growth. Other clues include the shape of the land beneath the sea, especially rift valleys, where the Earth's crust is splitting apart. There are also patterns in marine sediments that change from shallow water types to deep ocean types, showing how the basin deepened as the proto-ocean grew. But the birth of the Atlantic wasn't just a geological event, it had huge consequences for the planet's climate and life. The camp eruptions, which happened around 200 million years ago, released massive amounts of volcanic gases into the atmosphere, especially carbon dioxide and sulfur dioxide. These gases had powerful effects. The carbon dioxide caused global warming and made the oceans more acidic, harming marine life. Meanwhile, the sulfur dioxide led to short-term cooling by blocking sunlight with volcanic aerosols. After that cooling, the world likely warmed even more than before. Many scientists believe that this dramatic environmental chaos helped trigger the Triassic-Jurassic extinction event, one of the 5 biggest mass extinctions in Earth's history. While experts are still debating the exact chain of events, the timing matches well. The planet's ecosystems were already fragile, and these massive eruptions may have been the final blow that wiped out many species. In this sense, the beginning of the Atlantic Ocean was also the end of a world. As the proto-Atlantic widened, it began to change the world in other ways too. Before this, all the oceans had been part of one giant global ocean that surrounded the supercontinent Pangea. But once the new ocean opened up, it disrupted those currents. New ocean currents began to flow, carrying warm water and influencing global climates in new patterns. New coastlines formed, creating brand new habitats for marine life to evolve in. Over time, as the continents moved farther apart, the plants and animals living on them began to evolve in different directions, giving rise to the amazing diversity of life we see on different continents today. And this story isn't over. The Mid-Atlantic Ridge is still active. Even now, it creates new seafloor every year, slowly pushing North America, South America, Europe, and Africa farther apart. The Atlantic Ocean is still growing, just a few centimeters each year, but over millions of years it adds up. The powerful forces that shattered Pangaea and gave birth to this ocean are still at work today, shaping our world in slow but unstoppable ways. So the early Atlantic Ocean wasn't just a crack in the earth or a patch of water. It was the first sign that a mighty supercontinent was coming apart. The Central Atlantic Magmatic Province wasn't just a volcanic episode. It was the fiery announcement that the world was changing forever. This moment in Earth's history reveals how deep underground forces, volcanic eruptions, and the slow drift of continents are all part of the same long connected story. The Proto-Atlantic was a dramatic and often violent testing ground, where nature reshaped the planet's surface and began the slow process of sculpting the familiar map we know today. It was the final chapter in Pangea's life and the opening act of the Atlantic Ocean story, a story that is still being written beneath our feet. Before the mighty supercontinent called Pangaea began to break apart in a dramatic and slow-motion process, back in the deep reaches of the Triassic period, which started around 250 million years ago, the Earth's land looked and felt quite different from what we know today. Imagine one massive landmass stretching almost from the North Pole to the South Pole, a colossal piece of Earth's crust joined together like a giant puzzle. This land was not broken up by oceans like today's continents. It was mostly dry and had a harsh, continental climate, especially in the vast inner regions. These interior areas would have been dry like deserts and faced very hot summers and very cold winters. Meanwhile, the coastal areas, though still expansive, were somewhat milder, more humid, and had a more temperate feel. Because there were no huge oceans separating parts of the land, animals and plants could spread out across enormous distances. Species such as early dinosaurs, small furry cynodonts, relatives of mammals, and hardy plants could travel and grow freely across the continent. There were no massive seas acting as barriers to stop animals from mixing, or plants from spreading. This meant that life across Pangaea looked surprisingly similar from place to place. The planet, though physically large, was biologically more connected. For land animals and plants, the world felt smaller and more united, leading to fewer differences between species in different areas than we see today. But beneath this calm surface, deep inside the Earth, powerful forces were already at work. The rocky mantle beneath the crust moved slowly, stirred by currents of heat from the planet's core. These movements caused the giant continent of Pangaea to begin stretching, cracking, and eventually breaking apart. This did not happen all at once. It was a slow process that unfolded over tens of millions of years. The first signs of this great change appeared in the form of enormous cracks in the land, known as rift valleys. These rift zones were much like today's East African rift, but on a far bigger scale. Within these cracks, molten rock called magma pushed up from inside the Earth and spilled out as lava, forming vast fields of dark volcanic rock. These volcanic eruptions, known as flood basalts, changed the land and even affected the atmosphere. Although these early rift valleys had not yet become full-fledged oceans, they started to form physical barriers. Mountains could rise up along their edges, and deep valleys could make it harder for animals to move from one side to the other. As time passed, these rifts widened and sank lower, eventually dipping below sea level. This allowed seawater from the Great Panthalassic Ocean, the single vast ocean that surrounded Pangaea, to flow inward. Slowly, shallow seas filled the lowlands, creating narrow but significant water barriers across the once unbroken land. Even though these new seaways were sometimes just shallow and narrow, for land animals they were like massive oceans. Creatures that could not fly or swim long distances became isolated. Seeds could no longer blow across with the wind as easily, and even birds or insects might not cross over. In these ways, the land began to split, not just physically, but biologically. This growing separation led to one of evolution's most important forces, divergent evolution. When a group of animals or plants become split in two and can no longer breed with each other, they begin to change in different ways. Since they no longer share genes or face the same environment, their bodies, behaviours, and traits evolve separately. As the continents slowly drifted apart, some moved toward the equator, becoming hot and rainy, while others drifted toward the poles, growing colder and drier. Each new land mass had its own climate, different plants, different predators, and different challenges. Plants were especially affected. While Pangaea had supported wide-spreading plant types suited to a large unified climate, the splitting of continents gave rise to new environments. Some places got more rain, some became drier, and some had very different soil. This led to a wave of new plant species, each adapted to its local conditions. Around this time, flowering plants, or angiosperms, began to thrive. They evolved new ways to attract pollinators like insects or birds, and new ways to spread their seeds, depending on where they lived. For example, imagine a kind of fern that once grew all across Pangaea. When part of its habitat was separated by a new sea, the fern on one side might evolve to survive in dry soil, while the one on the other side might adapt to grow quickly in a rainforest. Over millions of years, they would become different species, even if they looked similar at first. Animals experienced even more dramatic changes. Take the early mammals, for instance. Back during Pangaea's time, they were small, mostly active at night, and lived in the shadow of dinosaurs. But as the continents broke apart, mammals began to evolve along different paths. One of the most famous examples of this split is between marsupials and placental mammals. Marsupials, animals like kangaroos that give birth to tiny young which grow in a pouch, became common in the southern continents of Gondwana, such as what would later become Australia and South America. Placental mammals, those whose babies grow longer inside the womb, dominated the northern continents, known as Laurasia, which included North America, Europe, and Asia. Because the growing oceans separated these groups, they evolved separately for tens of millions of years, leading to the incredible variety of mammals we see today. Even dinosaurs, the rulers of the Mesozoic era, felt the impact of this slow breakup. During the Triassic and early Jurassic periods, dinosaur species were quite similar across the world. But as the rifting grew and oceans began to widen, different dinosaur families started to evolve in isolation. For example, the giant long-necked sauropods and the heavily armoured stegosaurs became more diverse, each adapting to the different conditions on their continents. In the southern continents especially, a group of massive sauropods called titanosaurs became widespread. These giants took on a variety of forms and sizes, evolving differently from their northern cousins. Because they were separated by vast distances and oceans, each group developed its own special traits and survival strategies, shaped by the plants and predators they lived alongside. And it wasn't just the big, famous animals. Small creatures like insects, amphibians, and freshwater fish were also affected. Rivers that had once flowed smoothly across Pangaea were broken up. Fish that once lived in the same water now found themselves in completely new environments. Over time, they too evolved into new species. Amphibians, who rely on moist environments, struggled with the drier interiors and the new oceans that blocked their paths. As a result, distinct types of amphibians began to evolve on each continent. These changes in life were closely tied to major changes in the global climate. As continents drifted apart, they reshaped ocean currents and wind patterns. The Great Panthalassic Ocean became more complex as new seas like the Atlantic and Indian Oceans began to form. This changed how warm and cold waters flowed around the planet, leading to new climate zones. Some areas became wetter, growing rainforests, while others became dry and turned into deserts. Seasons also became more extreme in many places. Animals and plants had to adapt to these changes too, developing ways to survive long dry spells or cope with cold winters and hot summers. Volcanic activity from the rifting released greenhouse gases, warming the planet, while new oceans later helped pull carbon dioxide out of the air, cooling it again.